Right now, every diagram of the solar system you have ever seen is lying to you. Not through malice, not through carelessness. The planets in those diagrams are real. Their distances are measured. Their orbits follow the laws of physics with a precision that would make a watchmaker weep with admiration. The lie is not in what those diagrams show. The lie is in what they quietly, systematically, and completely leave out. What they leave out is almost everything. The image you carry in your mind right now, the one that formed in a classroom somewhere in your childhood, reinforced by 1,000 documentaries and textbook covers and animated explainers, that image shows you the solar system ending somewhere around Neptune. 8 planets, a bright sun at the center, and then darkness, the void, the silent gulf between stars. Clean, orderly, finished. That image captures less than 0.03% of the solar system's true radial extent. Read that again slowly. Less than 0.03%. Everything you have ever been shown, every planet, every moon, every asteroid belt, every spacecraft humanity has ever launched, every photograph ever taken of another world, all of it fits inside a region so cosmically insignificant relative to the actual solar system that rendering both to scale on a single image would be physically impossible. The planets would vanish, not shrink to a small dot, vanish, disappear below the threshold of visibility entirely, swallowed by the true dimensions of the structure surrounding them. There exists, beyond the planets, beyond every boundary you have heard described as the edge of the solar system, a structure so vast that it makes the entire planetary region look like a single period typed at the center of a page the size of a continent, a sphere of frozen darkness containing trillions of objects, extending outward from the sun for distances measured not in billions of miles, but in fractions of a light year, a structure whose outer boundary may reach more than 1/3 of the way to the nearest star, a structure that has been orbiting the sun, silently and invisibly, for 4.5 billion years, and that you have almost certainly never truly contemplated. It is called the Oort Cloud, and once you understand what it actually is, not the thumbnail description, not the footnote in a textbook, but the genuine scale and architecture and implications of this thing, you will never look at the solar system the same way again. The comfortable diagram will be gone. In its place will be something far stranger, far larger, and in its own frozen way, far more beautiful. If you enjoy journeys that dismantle everything you thought you knew about the universe and rebuild it into something more true, do me a small favor and hit that like button and subscribe. It genuinely helps this channel grow, and there is much more like this ahead. Get yourself comfortable. Clear your mind of the diagram you learned as a child. We are going somewhere that diagram was never designed to take you. Let's begin. Close your eyes and picture the solar system. You already know exactly what you will see. A bright yellow sphere at the center, radiating light in every direction. Circling it, in neat concentric rings, the planets. Mercury first, huddled close, grey and cratered. Then Venus, shrouded in pale cloud. Then Earth, blue and fragile. Then Mars, rust-colored and thin atmosphered. A gap scattered with rocky debris, the asteroid belt, and then the outer solar system opens up. Jupiter, banded and enormous. Saturn, ringed and pale gold. Uranus, tilted on its axis, a cold blue-green. Neptune, the deepest blue, the farthest planet, the last named world. Perhaps Pluto appears as a tiny dot at the very edge, a demoted world clinging to relevance. And then the image ends. Darkness closes in. The solar system is finished. You have seen this image so many times that it feels less like a picture and more like a fact. It feels like something you looked up rather than something someone drew for you. But someone drew it, and they made choices when they drew it. They chose what to include, they chose where to stop, and the place they chose to stop Neptune, or perhaps the heliopause, or perhaps a vague suggestion of outer darkness. That choice embedded itself in your understanding of your own cosmic address, so deeply that questioning it feels almost like questioning whether the sun is real. Begin at the sun. Our star is a sphere of plasma, roughly 865,000 miles across. fusing hydrogen into helium at its core at temperatures exceeding 27 million degrees Fahrenheit. Every single second, it converts approximately 4 million tons of matter directly into energy. That energy radiates outward across the solar system, diminishing with distance according to a precise mathematical law, warming and illuminating everything within its reach. Mercury orbits at roughly 0.39 astronomical units from the Sun, 1 astronomical unit being the average distance between Earth and the Sun, approximately 93 million miles. Venus follows at 0.72, Earth at exactly 1 by definition. Mars at 1,52. These 4 rocky worlds constitute the inner solar system, a compact and relatively warm zone where solid surfaces exist under intense enough sunlight to drive weather, chemistry, and in one extraordinary case, life. Light crosses the entire inner solar system in under 25 minutes. Beyond Mars lies the asteroid belt, a broad ring of rocky and metallic debris stretching from roughly 2.2 to 3.2 astronomical units. Despite its fearsome reputation in popular science fiction, the asteroid belt is mostly empty space. The total mass of everything in it, combined every rock, every metallic fragment, every dwarf planet, amounts to less than 4% of the Moon's mass. You could fly a spacecraft straight through the asteroid belt and have a very high probability of encountering nothing at all. Past the asteroid belt, the character of the solar system changes. The gas giants begin. Jupiter orbits at 5.2 astronomical units. It is so massive, containing more than twice the combined mass of every other planet in the solar system, that astronomers sometimes joke that the solar system consists of the Sun, Jupiter, and debris. Its gravity shaped the architecture of the entire planetary region during the solar system's formation, flinging smaller bodies inward and outward, carving the structure that persists today. Saturn follows at 9.5 astronomical units, its ring system extending outward in a flat disk of ice and rock that spans a distance wider than the gap between the Earth and the Moon. Uranus orbits at 19.2 astronomical units, tilted so severely on its axis that it essentially rolls around the Sun on its side, likely the result of a catastrophic collision early in the solar system's history. And then Neptune, the outermost planet, the cold blue giant at 30.1 astronomical units, circling the Sun once every 165 Earth years at a temperature of roughly -330 degrees Fahrenheit. At Neptune's distance, sunlight arrives 900 times fainter than it does on Earth. A solar panel that generates 1 kilowatt of electricity in your backyard would generate just over 1 watt at Neptune's orbit. This is where the familiar diagram ends, Neptune at 30 astronomical units. Beyond it, perhaps a small notation about Pluto at 39 astronomical units, classified since 2006 as a dwarf planet. And then darkness. For the vast majority of people who have ever learned anything about the solar system, this is the complete picture. The solar system is a collection of 8 planets orbiting a star, spanning a distance of roughly 30 astronomical units from center to edge. Clean, orderly, comprehensible, the kind of structure a human mind can hold without strain. But the solar system is not 30 astronomical units across. It is not 50, not 120, not 1000. The solar system, the full gravitational domain of the Sun, the complete territory over which our star holds objects in orbit, may extend to 100,000 astronomical units or beyond. Some estimates push the outer boundary to 150,000, even 200,000 astronomical units. At 100,000 astronomical units, you are approximately 1.5 light years from the Sun. Sunlight takes 1.5 years to reach that distance. Voyager 1, traveling continuously since 1977 at roughly 38,000 miles per hour, would need approximately 30,000 years to reach that boundary. 30,000 years. The entire span of recorded human history, from the earliest cave paintings at Lascaux to the smartphone in your pocket, covers roughly 40,000 years. Voyager 1 would need nearly that entire span just to exit the solar system. Let that sit for a moment before we continue. Because the journey outward from Neptune's orbit to the true edge of the solar system is not a short extension of the familiar diagram. It is a voyage into a completely different category of scale. And before we can take that journey honestly, we need to dismantle the most widely believed misconception in popular astronomy. In August of 2012, NASA's Jet Propulsion Laboratory made an announcement that traveled around the world within hours. After 35 years of continuous travel, the Voyager 1 spacecraft had crossed the heliopause, the boundary where the solar wind, that torrent of charged particles streaming outward from the sun, finally loses its pressure battle against the incoming flow of interstellar particles. Voyager 1 had entered interstellar space. The headlines were immediate and nearly universal in their framing. Voyager 1 has left the solar system. Humanity's most distant spacecraft has exited our cosmic neighborhood. For the first time in history, a human-made object has traveled beyond the solar system's edge. Millions of people read those headlines, absorbed them, and filed the information away as settled fact. The solar system ends somewhere around 120 astronomical units. We know this because Voyager 1 crossed the line. The story is complete. The story was not complete. It had barely started. What Voyager 1 crossed in August 2012 was the heliopause. This is a real and meaningful boundary in the study of solar wind physics. It marks the point where the sun's outflowing plasma can no longer push back against the pressure of the local interstellar medium, the diffuse gas and dust that fills the space between stars. Inside the heliopause, the environment is dominated by solar wind particles. Outside it, interstellar particles take over. The boundary is detectable. The Voyager instruments measured it precisely. But the heliopause is a boundary in plasma physics. It is not a gravitational boundary. It has nothing whatsoever to do with the sun's gravitational reach. Gravity does not stop at the heliopause. Gravity does not stop at 120 astronomical units, or 200, or 1,000. The sun's gravitational influence extends outward continuously, weakening with distance according to the inverse square law, but never reaching zero. And objects at enormous distances, tens of thousands of astronomical units, are still orbiting the sun, still gravitationally bound, still members of the solar system. The heliopause is where the solar wind stops blowing. The solar system's gravitational boundary is roughly 1,000 times farther out. Here is the analogy that makes this concrete. Imagine you are standing inside a house on a cold winter night. The heating system in your home pumps warm air through vents in every room. Somewhere near the front door, the warm air from your heating system meets the cold air pressing against the exterior of the house. There is a thermal boundary there, a zone where the warm interior air gives way to the cold exterior air. If you opened the door and walked outside until you could no longer feel your home's heating system affecting the temperature around you, you might declare that you had left your home. But you have not left your home. You have left the zone where your heating system can be felt. Your home's property line, the actual legal and physical boundary of your land, extends far beyond where the warm air stops, beyond the front walk, beyond the driveway, all the way to the street. The heliopause is where the sun's heating stops. The solar system's property line is the street. NASA knew this. The scientists who worked on Voyager 1 knew this. Many of the articles written about the crossing included careful qualifications, noting that Voyager had left the heliosphere, the bubble of solar wind, rather than the solar system per se. But those qualifications were quiet. The headlines were loud, and the loud version is the one that lodged in the public mind. Consider what this means for how most people currently understand their cosmic address. An entire generation of casual science followers received the message from a legitimate and celebrated scientific announcement that the solar system ends at roughly 120 astronomical units. That number is now anchored in millions of minds as the edge of home. The actual outer boundary of the solar system is between 800 and 1,600 times farther away. This is not a minor correction. It is not the difference between one number and a slightly larger one. It is the difference between thinking you live in a small apartment and discovering that you own a territory stretching from one side of a country to the other. The scale is so different that the original mental model must be discarded entirely, not revised. Discarded. Because no revision of the old picture can accommodate what is actually there. What is actually there begins with a question that astronomers have been answering for the better part of a century, not by traveling outward to look, but by reading the trajectories of visitors that the outer solar system sends inward toward the sun. Comets. Not all comets are alike. The ones that appear in our sky on regular, predictable schedules, Halley's Comet returning every 75 to 76 years, for example, are short-period comets. Their orbits are relatively compact, tilted only modestly relative to the plane of the planets, and their origin is well understood. Most of them come from the Kuiper belt, the region beyond Neptune extending to roughly 50 astronomical units, where gravitational nudges from the outer planets gradually push icy bodies into new trajectories that send them swinging through the inner solar system. But there is another category entirely: long-period comets. These objects arrive in our sky on orbits that take not decades but thousands, tens of thousands, sometimes millions of years to complete. They plunge toward the sun from immense distances, blazing briefly as solar heat vaporizes their frozen surfaces into spectacular tails, and then retreat back into the outer darkness on trajectories so elongated that they will not return for geological timescales. Some of them, orbital calculations suggest, are making their very first visit to the inner solar system. Objects that have been drifting in frozen darkness since before the first dinosaur walked the Earth, finally tumbling inward for the first time in their 4 billion-year existence. What makes these objects so revealing is not their appearance but their trajectories. Long-period comets do not arrive from one direction, they come from everywhere. Their orbital planes are tilted at every conceivable angle relative to the flat disk of the planets. Some arrive from directly above the solar system, others from directly below, some from the direction of Orion, others from the opposite side of the sky. Plot the most distant points of their orbits on a three-dimensional map, and the pattern that emerges is not a flat ring, not a disk, not any structure concentrated near the plane of the planets. It is a sphere, a vast, roughly spherical shell of source points surrounding the sun in every direction, at distances of tens of thousands of astronomical units. The comets are arriving from all directions because their source population is distributed in all directions, and the only geometry consistent with that pattern is a structure that envelops the entire solar system like an enormous, hollow, three-dimensional shell. The mathematics does not permit another interpretation. The comets demand a spherical reservoir. They arrive as proof of its existence, frozen fragments of a population we have never seen, sent tumbling inward by forces operating at the outermost edge of the sun's domain. In 1950, a Dutch astronomer named Jan Hendrik Oort sat down with the orbital data of 19 long-period comets and looked for a pattern that others had missed. Oort was 43 years old, a careful and systematic thinker who had already made significant contributions to the understanding of the Milky Way's structure. What he noticed in the comet data was the clustering of aphelion distances, the most distant orbital points of these 19 objects, in a specific range around 20,000 to 50,000 astronomical units from the Sun. The clustering was too tight to be random. It pointed toward a real structure at a real distance, a reservoir, a cloud. He was not quite the first to propose such a structure. In 1932, the Estonian astronomer Ernst Öpik had independently suggested that a distant reservoir of comets might exist at the solar system's outer edges. But Öpik's proposal lacked the statistical foundation that Oort built. Oort had the numbers, the orbital data, the systematic analysis. He published his findings in the Bulletin of the Astronomical Institutes of the Netherlands, laying out the case for a vast spherical cloud of icy bodies orbiting the Sun at extreme distances, continuously resupplied by the comets that managed to reach visible altitudes and continuously drained by the comets that were destroyed in close solar passages. The structure was eventually named the Oort Cloud in his honor, and in the 75 years since that paper was published, every new line of evidence, every new comet measured, every new computer simulation of solar system dynamics, every new spacecraft measurement has strengthened the case for its existence. The Oort Cloud is not a speculation, it is not a guess. It is the only structure that can explain the comets currently arriving in our sky. But knowing it exists is not the same as understanding what it is. And understanding what it is requires confronting numbers that the human mind was not evolved to process naturally. What comes next will require you to rebuild your sense of scale from the ground up. Beyond Neptune, the solar system does not end, it transforms. This is the part of the journey that most diagrams skip entirely, not because the territory is unimportant, but because it is inconvenient. It does not fit on a poster. It does not compress neatly into an animation. It exists in a region so far from the sun that the human mind begins to lose its grip on the distances involved, and the temptation for any educator, any documentary maker, any science communicator is to simply stop the picture at Neptune and allow the darkness to close in. The solar system is done. We have reached the edge, move on. But the edge is not there. To find where the solar system actually ends, you must first understand what lies between Neptune and the Oort Cloud. Because that intermediate territory, largely unknown to most people, poorly mapped even by professional astronomers, is itself a revelation. It contains structures and objects that would each deserve their own documentary, their own chapter in the story of the solar system. And it contains one object in particular, whose existence was so difficult to explain that it quietly shook the foundations of how planetary scientists understood the outer solar system's history. Start just beyond Neptune's orbit. At roughly 30 to 50 astronomical units from the Sun lies the Kuiper Belt. Named after the Dutch-American astronomer Gerard Kuiper, though he predicted its absence rather than its presence, the structure was independently predicted by Irish astronomer Kenneth Edgeworth in 1943 and American astronomer Frederick Leonard in 1930, and was not confirmed to exist until 1992, when astronomers David Jewett and Jane Liu discovered the first Kuiper Belt object beyond Pluto of Hawaii's 2.2-meter telescope on Mauna Kea. They had been searching for 3 years. The Kuiper Belt is a broad, flattened disk of icy and rocky bodies concentrated near the plane of the planets. Pluto, reclassified as a dwarf planet in 2006, orbits within it at roughly 39 astronomical units. So does Eris, a world slightly smaller than Pluto that sparked the reclassification debate. So do Makemake and Haumea, and thousands of smaller objects with names drawn from mythology and the catalogues of minor planets. NASA's New Horizons mission, which flew past Pluto in July 2015, and the Kuiper Belt object Arakoth in January 2019, gave humanity its first close look at this remote population. The images it returned were extraordinary. Pluto revealed mountains of water ice towering 3 miles high, a vast heart-shaped plain of nitrogen ice called Tumbor Regio, and evidence of geological activity in a world that had no business being geologically active at its age and size. Arakoth, a contact binary object, 2 lobes that had gently merged in the early solar system, showed a surface so pristine and undisturbed that it read like a direct message from the formation era of the planets themselves. But the Kuiper Belt, remarkable as it is, extends only to roughly 50 astronomical units. It is a porch, a remarkable porch, but a porch nonetheless. Beyond it lies the scattered disk, a population of icy bodies flung into highly elliptical orbits by gravitational interactions with Neptune during the solar system's early history. Scattered disk objects occupy a broad and irregular region extending from about 30 astronomical units at their closest approach to the Sun out to several hundred astronomical units at their farthest. They are the refugees of the outer solar system, objects whose original orbits were disrupted and reshaped by the gravitational upheaval of the planet formation era, sent careening into trajectories that carry them in long, slow loops between the inner and outer reaches of the solar system. One scattered disk object in particular deserves attention. Eris, at its most distant point, swings out to roughly 97 astronomical units from the Sun. Light from the Sun takes over 13 hours to reach it at aphelion. It is frigid, isolated, and barely illuminated, yet it is still relatively close compared to what comes next. At 120 astronomical units lies the heliopause, the boundary that generated those global headlines in 2012 and 2018 when Voyager 1 and Voyager 2 crossed it respectively. We have already established what that boundary actually represents, a change in the local plasma environment, not a gravitational edge. But it is worth dwelling for a moment on just how staggering even this non-boundary is. 120 astronomical units, over 11 billion miles. Light takes roughly 16.5 hours to cross that distance. At highway speed, driving continuously without pause, the journey would take approximately 21,000 years. And yet Voyager 1, launched in 1977, covered this distance in 35 years of continuous travel at 38,000 miles per hour. When it crossed the heliopause, it was moving faster than any other human-made object in history. And it had traveled, by the standards of the true solar system, essentially nowhere. To understand just how little distance Voyager had covered by the time it crossed the heliopause, consider this single comparison. If the outer edge of the Oort Cloud sits at 100,000 astronomical units, then the heliopause at 120 astronomical units represents roughly 0.12% of the journey to the solar system's true boundary. Voyager 1 crossed what the headlines called the edge of the solar system, while still standing in the metaphorical front hallway of a structure that extends for 1,000 times that distance. The heliopause is step 1 of 1,000 steps, and the headlines declared the journey complete. Beyond the heliopause, in the vast and poorly understood region between roughly 120 and several thousand astronomical units, the solar system grows quieter and stranger. This is territory that no spacecraft has ever reached, no telescope has ever mapped in detail, and no human instrument has ever sampled directly. It is known almost entirely through inference, through the orbital statistics of objects that have been nudged out of it and sent tumbling inward, and through the mathematical models of planetary scientists who have spent careers simulating what must be there. But occasionally, an object is discovered that exists in this intermediate region and refuses to fit neatly into any existing category. An object whose very presence demands an explanation that the known physics of the solar system cannot comfortably provide. Such an object was discovered on the night of the 14th of November 2003. The astronomers were Mike Brown, Chad Trujillo, and David Rabinowitz, working with the Samuel Oschin telescope at the Palomar Observatory in California. They were conducting a systematic survey of the outer solar system, searching methodically through images of the sky for the characteristic slow drift of a distant solar system object against the fixed background of stars. They had found many Kuiper Belt objects before. They were looking for more. What they found instead was something that had no business being where it was. The object was eventually named Sedna, after the Inuit goddess of the sea, who was said to live in the cold darkness of the Arctic Ocean floor. The name was fitting in ways its discoverers could not have fully anticipated. Sedna is one of the coldest, most isolated, most darkness-dwelling objects ever found in the solar system. Its surface temperature hovers around -400 degrees Fahrenheit, making it one of the coldest places in the known solar system. It reflects roughly 32% of the faint sunlight that reaches it, suggesting a surface of pale ice and organic compounds reddened over billions of years by cosmic radiation. But Sedna's appearance was not what made it significant. What made it significant was its orbit. Sedna's closest approach to the Sun, its perihelion, is approximately 76 astronomical units. Its farthest point, its aphelion, stretches to roughly 937 astronomical units. It takes approximately 11,400 years to complete a single orbit. An observer standing on Sedna's surface at its closest approach to the Sun would see a star so small and faint that it would be difficult to locate without prior knowledge of where to look. The Sun from Sedna's perihelion is roughly 100 times smaller in angular diameter than it appears from Earth. You could cover it with a pinhead held at arm's length, and that is its closest approach. Here is the problem that Sedna immediately posed to planetary scientists. Its perihelion distance is 76 astronomical units, well beyond Neptune's orbit at 30 astronomical units. This means Neptune's gravity cannot have placed Sedna in its current orbit through ordinary gravitational scattering. For Neptune to scatter an object outward, the object must pass close enough to Neptune to feel its gravitational influence significantly. An object with a perihelion of 76 astronomical units never comes anywhere near Neptune. It is too far away. Neptune cannot reach it. But something moved Sedna into this orbit. Something shaped a perihelion of 76 astronomical units at the closest approach, and an aphelion pushing nearly 1,000 astronomical units at the farthest. Something with sufficient gravitational influence to reshape the orbit of a world-sized body at distances far beyond the reach of the known planets. The leading candidates were three. First, a close stellar passage during the early solar system, another star passing within perhaps a few hundred to a few thousand astronomical units of the Sun during the era when the solar system was still embedded in its birth. Cluster, gravitationally tugging Sedna's orbit into its current extreme configuration. Second, the galactic tide, the combined gravitational influence of the Milky Way's mass, slowly raising Sedna's perihelion during the early epochs of solar system formation. Third, and most dramatically, an as yet undiscovered massive planet in the outer solar system, a world several times the size of Earth, orbiting at hundreds or thousands of astronomical units, whose gravity has sculpted Sedna's trajectory, along with the trajectories of several other similarly detached objects. This third hypothesis, sometimes called Planet 9, though it remains unconfirmed, has generated considerable scientific debate in the years since Brown, and colleagues noted that several extreme trans-Neptunian objects appeared to have their orbits clustered in ways that a distant massive planet could explain. The hypothesis is genuine and taken seriously by a number of planetary scientists. The counter-arguments are also serious. What appears to be orbital clustering may be a statistical artifact of observational bias. The telescopes that find these objects are pointed at specific patches of sky, not uniformly across the entire celestial sphere. As of 2026, no direct detection of Planet 9 has been made, and the debate continues. But regardless of which explanation proves correct for Sedna's orbit, the object's existence confirmed something profound. The region between the Kuiper belt and the inner Oort Cloud is not empty. It is not a transition zone too remote to contain anything interesting. It contains objects on orbits so extreme, shaped by forces so distant and so poorly understood, that their very existence pushes at the boundaries of current solar system science. Sedna is a boundary object. It inhabits the transition zone between the known solar system and the inner Oort Cloud, occupying a region that was not supposed to contain anything noteworthy, and it is not alone. In 2012, the object 2012 VP113 was discovered by astronomers Scott Shepard and Chad Trujillo using the dark energy camera at the Cerro Tololo Inter-American Observatory in Chile. It follows a similarly detached orbit with a perihelion of roughly 80 astronomical units and an estimated orbital period exceeding 4,000 years. Its discoverers nicknamed it Biden at the time of discovery. Its trajectory, like Sedna's, places it in the same inexplicable intermediate region too close for the outer Oort Cloud, too far for Neptune's influence. Additional detached trans-Neptunian objects have continued to appear in sky surveys. Each one populates the same strange intermediate territory. Each one adds a data point to a growing picture of a continuum, a connected, graduated structure extending from the Kuiper belt through the scattered disk, through the detached population where Sedna and its companions drift, into the Hills cloud of the inner Oort region, and outward into the full outer Oort cloud beyond. There is no gap, there is no clean transition. The solar system does not organize itself into neat compartments with empty space between them. It flows outward continuously, growing sparser and stranger with distance, its populations shading into one another without clear boundaries. To build a true sense of the distances involved between Neptune's orbit and the threshold of the Oort cloud, you need a different relationship with the numbers, not just their magnitude, but their texture. Not just how large they are, but what they mean for objects and light and time. Neptune sits at 30 astronomical units. 1 astronomical unit equals roughly 93 million miles. 30 times that is 2.79 billion miles. Light covers that distance in about 4 hours and 10 minutes. It is a vast distance by any human standard. The fastest commercial aircraft ever built, the Concorde, flying continuously at its top speed without pause, would need roughly 640 years to reach Neptune. Sedna's aphelion, its farthest point from the Sun, at roughly 937 astronomical units, is more than 31 times farther than Neptune. It sits approximately 87 billion miles from the Sun. Sunlight needs roughly 5.5 days to reach it. The Concorde, still flying without pause, would need nearly 20,000 years. Sedna is an object in our solar system, and it takes the fastest airliner ever built 20 millennia to reach its most distant orbital point. Yet Sedna's aphelion at 937 astronomical units does not even reach the inner threshold of the Hills cloud, the denser inner region of the Oort cloud that begins somewhere around 2,000 astronomical units from the Sun. Sedna's farthest point is less than halfway to where the Oort cloud begins. Pause on that for a moment. An orbit so extreme that it takes 11,400 years to complete, carrying an object to 87 billion miles from the Sun, does not even reach the inner edge of the outer solar system's dominant structure. At 2,000 astronomical units where the Hills cloud begins, sunlight takes roughly 11.5 days to arrive. An object orbiting at this distance moves so slowly that it covers ground at a pace roughly equivalent to a brisk walk relative to the size of its orbit. It is gravitationally tethered to a star. It can barely identify as anything more than an exceptionally bright point of light. Now, consider what it would mean to communicate with a spacecraft at this distance. Radio signals, like light, travel at approximately 186,000 miles per second. A signal transmitted from Earth to a spacecraft at 2,000 astronomical units would take roughly 11.5 days to arrive. The spacecraft's reply would take another 11.5 days to return. A simple exchange, one instruction, one acknowledgement, would span 23 days of silence. Any scientist directing the mission would transmit a command and then wait nearly 3 weeks to learn whether it had been received and executed. This is for the inner edge of the Hills cloud, the beginning of the Oort cloud's inner region. Push the spacecraft to the outer Oort cloud at 100,000 astronomical units, and the communication delay becomes devastating in a way that transcends mere inconvenience. A signal sent to a spacecraft at that distance would take approximately 1.5 years to arrive. The spacecraft's reply would take another 1.5 years to return. 3 years between a question and its answer. If something went wrong, if an instrument failed, if the spacecraft began tumbling, if a critical system stopped responding, mission controllers on Earth would not learn about it until 18 months after it had happened. Any corrective command they sent in response would not arrive until another 18 months had passed. 3 years of helplessness. 3 years during which the spacecraft would be entirely on its own, operating without human guidance in the darkest, coldest, most remote region of the solar system. This is not a problem that a faster computer or a better antenna can solve. It is a consequence of the finite speed of light. The universe imposes this limit absolutely. No signal can travel faster. No future technology will change the arithmetic. The outer Oort cloud is so remote that even light, the fastest messenger the universe permits, cannot bridge the distance in less than a year. The heliopause generated headlines when Voyager 1 crossed it in 2012. But there is another boundary beyond the heliopause that is less well known to the general public and far more physically significant in terms of understanding the outer solar system. It is called the heliosheath termination shock. And then beyond that, as you continue outward, the bow shock, the region where the sun's motion through the interstellar medium begins to compress the interstellar gas ahead of it. But neither of these is the boundary that matters most for the story of the Oort cloud. What matters most is a region that has no official name, no clear detection threshold, no spacecraft measurement. It is the transition zone where the solar system's gravitational dominance slowly yields to the combined gravitational influence of the surrounding galaxy. The zone where objects are still orbiting the sun, technically, but their allegiance is becoming uncertain, where a passing star or the galactic tide could, with only a modest perturbation, sever the gravitational thread and send an object drifting into the interstellar medium. This zone does not begin at 120 astronomical units. It does not begin at 1,000. It begins, in any meaningful sense, at the outer reaches of the Oort Cloud itself, tens of thousands of astronomical units from the Sun. And understanding what governs that zone requires understanding forces that do not originate in the solar system at all, forces that originate in the galaxy. But before we confront those forces, before we examine the architecture of the Oort Cloud in full and the mechanisms that shape and sustain it, we need to sit for one more moment with the distance between Neptune and the inner Oort Cloud. Because this intermediate region, roughly 30 to 2,000 astronomical units, contains not just Sedna and its companions, but an entire population of detached and transitional objects whose existence tells a story about the solar system's violent early history. A history that explains how the Oort Cloud was built in the first place. That story involves planets moving, not slowly, not gradually, but in a period of dramatic and catastrophic orbital migration that reshaped the entire outer solar system within the first few 100 million years of its existence. It involves Jupiter flinging objects outward like a cosmic slingshot. It involves Neptune carving a path through a disk of primordial ice and rock, scattering debris in every direction. It involves the Sun's birth cluster, the dense stellar nursery, where our star formed, providing a gravitational environment so different from today's relative isolation that objects scattered to enormous distances were gently caught and held rather than lost to interstellar space. It is a story of catastrophe that produced one of the solar system's most enduring structures. And it begins, as most stories of cosmic violence do, with forces of almost incomprehensible scale being applied to objects of almost incomprehensible number over timescales that dwarf the entirety of human history. We are just getting started. There is a particular kind of darkness that exists only at the edge of the solar system. Not the darkness of a room with the lights off, not the darkness of a forest at midnight. Those darknesses are temporary, local, penetrated by the faintest ambient glow from distant cities, from starlight filtering through atmosphere, from the biological warmth of living things nearby. Those darknesses are comfortable in the way that all familiar things are comfortable, even when they are frightening. The darkness at the outer solar system is different in kind. It is a darkness that has not been interrupted for 4.5 billion years. A darkness in which the Sun, still the dominant star in the sky, provides no more warmth than a distant campfire glimpsed from the wrong side of a mountain range. A darkness so complete and so cold that the objects drifting through it have been frozen, motionless in any practical sense, since before the first complex life appeared on Earth. But occasionally, something disturbs that darkness. A gravitational nudge, a passing star's distant influence, the slow, patient work of the galaxy's tidal forces on an orbit that has grown just slightly too elliptical to maintain its ancient equilibrium. And when that happens, one of those frozen objects begins to fall. Not dramatically, not quickly. Over thousands of years, the fall is imperceptible, but the direction has changed. The trajectory has been altered. What was a stable, ancient orbit has become something new, a plunging arc that carries the object inward, through the outer solar system, through the scattered disk, past the giant planets, closer and closer to a star it has never approached before. And then, somewhere inside the orbit of Jupiter, something extraordinary happens. The Sun's heat, still faint by any earthly standard, reaches the object's frozen surface with enough intensity to begin vaporizing the outermost layer of ice. Carbon dioxide and water and methane and ammonia, locked in crystalline form for billions of years, suddenly sublimate, converting directly from solid to gas, and stream outward from the object's surface in a glowing cloud of vaporized material. Dust particles trapped in the ice are released and swept backward by the faint but steady pressure of sunlight and solar wind. A tail forms, then two tails, one of dust, curving gracefully along the object's orbital path, one of ionized gas, blown straight back from the Sun regardless of the direction of motion. always pointing directly away from the star. A comet is born, and in that moment of blazing, brief visibility, perhaps a few weeks, perhaps a few months of brightness in our sky before the object swings around the sun and retreats back into the darkness, it delivers something far more valuable than spectacle. It delivers information. Every long-period comet that arrives in the inner solar system is a messenger. Its trajectory, measured with precision by telescopes around the world and in orbit, encodes the address of its origin, the shape of its orbit, the orientation of its path through the sky, the calculated distance of its most remote orbital point, the aphelion. All of these parameters speak directly to where the object came from, how long it has been falling, and what region of the outer solar system dispatched it. And for decades, astronomers have been reading those messages, accumulating them, cross-referencing them, building from them a statistical portrait of a structure they cannot see directly, but can infer with extraordinary confidence from the trajectories of its emissaries. The structure those trajectories reveal is the Oort Cloud. To understand why long-period comets are such powerful evidence for the Oort Cloud's existence, you need to understand what makes them different from their short-period counterparts. Short-period comets, objects like Halley's Comet, with an orbital period of roughly 75 to 76 years, or Comet Encke, which returns every 3.3 years, follow orbits that are relatively compact and concentrated near the plane of the planets. Their inclinations, the angles at which their orbits tilt relative to the flat disk of the solar system, are modest. Most short-period comets orbit in the same general direction as the planets, and crucially, their aphelia, their most distant points, cluster in the region of the outer planets, consistent with an origin in the Kuiper belt or the scattered disk. The physics of their origin is understood. The giant planets, particularly Neptune and Jupiter, gravitationally perturb Kuiper belt objects over millions of years, occasionally nudging them into new trajectories that carry them repeatedly through the inner solar system. These nudged objects become short-period comets. Their source population is known, mapped, and visited by spacecraft. Long-period comets are entirely different in every measurable parameter. Their orbital periods exceed 200 years by definition, and typically range from thousands to hundreds of thousands of years. Some have calculated orbital periods extending to millions of years. Their aphelia sit not in the Kuiper belt region but at distances of tens of thousands of astronomical units in a few cases, exceeding 100,000 astronomical units, and their orbital inclinations are not concentrated near the plane of the planets. They are randomly distributed across the full sphere of possible orientations. This last point is the most critical. A short-period comet arrives from somewhere in the general direction of the ecliptic plane, the flat disk, where the planets orbit. You can roughly predict what part of the sky a short-period comet will emerge from based on the geometry of the Kuiper belt. Long-period comets arrive from every direction with equal probability. Above the ecliptic and below it, from the direction of Orion, and from the direction of the Southern Cross, from the North Celestial Pole, and from the galactic center. No preferred direction, no concentration in any region of the sky. Think carefully about what this means geometrically. If long-period comets originated from a flat disk like the Kuiper belt, they would show a preference for arriving from directions near the ecliptic plane, just as short-period comets do. The flat geometry of their source population would imprint itself on their arrival directions. The fact that they show no such preference, that they arrive with equal probability from every direction in the three-dimensional sky, means their source population is not flat. It cannot be flat. The only geometry consistent with uniformly distributed arrival directions is a sphere, a three-dimensional shell surrounding the sun, from all sides equally, sending comets inward from every direction with no preferred orientation. The sphere is the Oort Cloud, and the comets are its proof. Jan Oort saw this in 1950, working with 19 comets and a calculating machine that would embarrass a modern pocket calculator. He plotted the aphelia. He noted the clustering at vast distances. He recognized the random inclination distribution for what it was, a signature of spherical geometry, and he proposed a structure that, at the time, was entirely beyond the reach of any observational confirmation. He was working purely from orbital mechanics, from the trajectories of objects that had already traveled hundreds of thousands of astronomical units to reach him, from the frozen messages those objects carried about the place they had left behind. It was an act of extraordinary scientific inference, the equivalent of determining the shape, size, and population of a distant forest by analyzing the direction and origin of leaves that blow into your yard, never having seen the forest itself. The forest is real, the leaves prove it. The comets that have arrived in our sky over the centuries are not abstractions. They are specific objects with specific names, specific trajectories, specific compositions, and specific stories. Each one carried a history written in ice, a chemical record of the primordial solar system, preserved in frozen form for billions of years, and briefly revealed as the sun's heat vaporized the outermost layers. Consider Comet Hale-Bopp. On the night of the 22nd of July 1995, two astronomers independently discovered a new comet within minutes of each other. Alan Hale, a professional astronomer in New Mexico, was conducting a routine observation of known deep sky objects when he noticed an unfamiliar fuzzy smudge near the globular cluster Messier 70. Thomas Bopp, an amateur astronomer in Arizona, was at a star party in the desert when he spotted the same object through a friend's telescope. Both reported their discovery to the Central Bureau for Astronomical Telegrams within the same hour. The comet was unusually bright for its distance. It was already generating a substantial coma, despite being located beyond Jupiter's orbit, still more than 600 million miles from the Sun. Astronomers recognized immediately that when it reached perihelion, its closest approach to the Sun, it would be spectacular. They were right. Hale-Bopp reached perihelion in April 1997 and became one of the most widely observed comets of the 20th century. It was visible to the naked eye for a record 18 consecutive months. Its twin tails, one white dust tail curving gracefully along its orbital path, one blue ion tail pointing straight away from the Sun, made it one of the most photographed objects in the night sky in the history of photography. Hundreds of millions of people on every continent saw it. But what Hale-Bopp meant scientifically was more significant than its visual spectacle. Before its visit to the inner solar system, Hale-Bopp's orbit carried it to an aphelion of roughly 370 astronomical units from the Sun, with an orbital period of approximately 2,520 years. This places its most distant point in the transition region between the scattered disk and the inner Hills cloud, a region that had, until the discovery of Sedna 8 years later, been largely depopulated in the scientific imagination. Hale-Bopp was a visitor from a region that most people did not know existed, an object that had last entered the inner solar system roughly 4,200 years ago, when ancient Egyptians were constructing the pyramids at Giza, and that had spent the intervening millennia drifting back outward through a darkness almost incomprehensible in its scale. Its chemical composition told additional stories. Spectroscopic analysis revealed the presence of water, ice, carbon monoxide, carbon dioxide, methane, ammonia, formaldehyde, and numerous complex organic molecules in its coma. Some of these compounds, particularly the complex organics, were present in concentrations that surprised researchers. Hale-Bopp became one of the most chemically studied comets in history, and its composition provided a direct window into the chemistry of the primordial solar system at the time of its formation. The molecules it released as it vaporized near the Sun had been frozen since before the first multicellular life appeared on Earth. It was a chemical fossil, a time capsule from the formation era of the planets, delivered directly to our doorstep. Now consider Comet Hyakutake. In January 1996, a Japanese amateur astronomer named Yuji Hyakutake was conducting a comet survey from his home in Kagoshima Prefecture, Japan, using a pair of large binoculars. On the night of January 30th, he spotted a faint, fuzzy object that had not been there in previous nights. He reported it. Confirmations came quickly. Orbital calculations followed, and those orbital calculations revealed something that made the astronomical community pause. Hyakutake's pre-discovery orbit, the trajectory it had followed before entering the inner solar system, carried it to an aphelion estimated at somewhere between 1,000 and 2,000 astronomical units from the Sun. Its orbital period before the current visit was calculated at roughly 15,000 to 30,000 years, placing its most distant orbital point in the inner Hills cloud region of the Oort Cloud. This was a genuine Oort Cloud messenger, an object that had spent tens of thousands of years drifting in the frozen darkness beyond the scattered disk, finally nudged inward by forces operating at the solar system's outermost edge, making its first approach to the inner solar system in geological time. When Hyakutake reached its closest approach to Earth on the 25th of March 1996, it passed within roughly 9.5 million miles of our planet, one of the closest cometary approaches in recorded history. It was briefly one of the brightest objects in the night sky, its tail stretching across more than 90 degrees of the celestial sphere under dark skies. X-ray emissions from the comet, detected by the ROSAT satellite, were the first ever observed from a comet, an unexpected discovery that opened an entirely new field of cometary science. But its composition was what made it scientifically transformative. Hyakutake was extraordinarily rich in ethane and other complex organic molecules. The ratio of deuterium to hydrogen in its water ice was measured and found to be roughly twice that of Earth's ocean water, a result that complicated the hypothesis that comets delivered the bulk of Earth's water during the heavy bombardment era. The comet was telling scientists something about its origin. Its chemistry was the fingerprint of a specific region of the primordial solar disk, where it had formed before being scattered outward to the Oort Cloud. After its passage, gravitational interactions with Jupiter reshaped Hyakutake's orbit dramatically. Its new aphelion was calculated at roughly 3,400 astronomical units, and its new orbital period extended to approximately 70,000 years. It will not return to the inner solar system for 70 millennia. When it does, if it does, comets can be destroyed, scattered by planets, or flung out of the solar system entirely. During inner solar system passages, it will find a solar system that may be recognizable in its basic architecture, but utterly transformed in the details. Every civilization that has ever looked at the night sky, every language that has ever developed on Earth, every species that has arisen and gone extinct in the interim, all of it will have happened between Hyakutake's departure and its return. Beyond Hale-Bopp and Hyakutake, the catalogue of long-period comets extends to hundreds of confirmed objects, each one an emissary from a different region of the outer solar system, each one carrying slightly different information about the reservoir that dispatched it. Some comets arrive on trajectories calculated. These objects are sometimes called dynamically new comets, meaning they appear to be making their very first ever visit to the inner solar system. Their surfaces have never been warmed by the sun before. Their ice has never sublimated. Their chemical composition is as pristine as anything that has existed since the solar system formed. When a dynamically new comet is detected approaching the sun for the first time, astronomers experience something that has no precise parallel in other fields of science. They are receiving a direct physical sample, albeit a distant one from the solar system's formation era. The molecules in that comet's coma were synthesized in the protoplanetary disk 4.5 billion years ago, frozen into the comet's nucleus as it was assembled from the raw material of the early solar system, and preserved in near absolute zero darkness for the entirety of Earth's history. The comet is older than life, and it has traveled, in some cases, more than 50,000 astronomical units over 4.5 light years to deliver its ancient chemical message to the telescopes of a civilization that has existed for an eye blink of geological time. Among the most recently studied of these messengers is Comet C 2025 R3, designated by the Minor Planet Center, following its discovery in September 2025. Detected initially by the Pan-STARRS survey telescope on Haleakala in Hawaii, the same facility that had contributed to numerous outer solar system discoveries. C 2025 R3 drew immediate attention because of its steep orbital inclination. Its trajectory approached the inner solar system at an angle far above the plane of the planets, precisely the kind of high-inclination orbit expected of an object whose origin lies in the spherical Oort Cloud rather than the flattened Kuiper belt. c. 2025 R3 reached perihelion in April 2026 at a distance of roughly 47 million miles from the Sun, passing inside Mercury's orbit and developing a visible tail detectable from Earth's surface under dark skies. Its full orbital period remains uncertain because only a relatively short arc of the orbit has been observed. Current estimates suggest a period measured in thousands of years, consistent with an origin in the inner Oort Cloud region. As more observations accumulate and the orbital solution is refined, its aphelion distance will be calculated with greater precision, adding another data point to the growing statistical portrait of the structure that sent it. Each new long-period comet strengthens the same picture that Jan Oort built from 19 data points in 1950. Each new trajectory, each new aphelion distance, each new inclination measurement randomly distributed across the sky, clustering at vast distances, consistent only with a spherical source population at tens of thousands of astronomical units, tightens the statistical case for the Oort Cloud's existence and refines the estimates of its size, its population, and its internal structure. The comets are the cloud's autobiography, written in ice and trajectory, mailed inward from the darkness over millions of years, arriving, one by one, in the warm inner solar system where their ancient chemistry briefly blazes before they retreat back into the cold. But there is one more thing about long-period comets that deserves careful attention because it speaks not just to the Oort Cloud's existence but to its longevity and its continuous activity. Comets are not permanent. Each time a long-period comet passes through the inner solar system, the Sun's heat vaporizes a layer of ice from its surface. The comet loses mass with every perihelion passage. After enough passages, the number varies depending on the comet's size and composition, and the distance of its closest approach to the Sun. The comet is effectively destroyed. Its volatile ices are exhausted. What remains, if anything, is a dark, inert rocky nucleus indistinguishable from an asteroid, or the object disrupts entirely, breaking apart into a swarm of debris that disperses along its orbital path over centuries. A comet that makes one pass through the inner solar system per orbital period, with a period of 10,000 years, makes roughly 450,000 passes over the solar system's 4.5 billion year lifetime. In reality, most long-period comets do not survive nearly that many passes. Many are destroyed in their first few visits. Some are ejected from the solar system entirely by close encounters with Jupiter during their initial passage through the inner solar system. Others are disrupted by tidal forces as they swing around the Sun. The population of long-period comets in the inner solar system is therefore being continuously depleted. Objects are consumed, destroyed, or ejected on every pass. And yet, century after century, new long-period comets keep arriving. The supply does not dry up. The rate of new arrivals remains roughly constant across all of recorded astronomical history. This constancy is itself a profound statement about the Oort Cloud. For the supply of new comets to remain steady across 4.5 billion years, the reservoir must be enormous. Not just large enough to supply comets at the current rate for another century or another millennium, but large enough to sustain that rate continuously across a timescale equal to the entire age of the solar system. The mathematics of this constraint demands a population of at least several hundred billion objects in the source reservoir, and models suggest a population closer to 1 trillion, possibly considerably more. 1 trillion objects, each one a frozen mountain of ancient ice and rock, each one drifting in isolation through near absolute darkness at distances of thousands to tens of thousands of astronomical units from the Sun, each one waiting in its ancient orbit for the gravitational perturbation that will send it tumbling inward. The steady arrival of comets in our sky is not a spectacle, it is a census, a continuous readout from a structure so vast and so populated that it can sustain 1 trillion objects, losing members to destruction and ejection for billions of years without running dry. The lights in our sky are the Oort Cloud breathing, Each comet is an exhaled breath, a fragment of the solar system's outermost structure released inward, blazing briefly, and gone. The cloud breathes slowly, on timescales of millions of years, but it breathes continuously. And it has been breathing since before the first fish swam in Earth's ancient seas. That breathing has a mechanism, a set of forces operating not from the solar system's center, but from its edges and from the galaxy itself. Forces that reach across light years of space to nudge frozen objects in orbits so remote that the sun is merely a bright star. Forces that have been shaping the Oort Cloud's population since the solar system was young. Understanding those forces requires looking outward past the Oort Cloud entirely to the structure that contains our solar system the way the solar system contains its planets, the Milky Way. 4.5 billion years ago, the solar system did not exist. In its place was a cloud, not the Oort Cloud. That structure had not yet been built. What existed instead was a vast, slowly rotating nebula of gas and dust, roughly a light year or two across, drifting through an arm of the Milky Way that would eventually be called the Orion Spur. The cloud was mostly hydrogen and helium, the primordial material of the universe, laced with trace amounts of heavier elements forged in the cores of stars that had lived and died in the billions of years before the sun existed. Something disturbed that cloud. Perhaps a nearby supernova sent a shockwave rippling through the nebula, compressing it beyond the threshold at which gravity could take hold. Perhaps it was simply the slow accumulation of its own mass over millions of years, gradually densifying until collapse became inevitable. Whatever the trigger, the cloud began to fall inward on itself. As it collapsed, it spun faster, the same physics that makes a figure skater spin faster when she pulls her arms inward. The center grew hot. The edges flattened into a disk, and at the center of the collapsing disk, a protostar ignited. The sun was born. Around it, the remaining gas and dust settled into a vast, flat, protoplanetary disk, extending outward for hundreds of astronomical units. Within this disk, solid particles began to collide and stick together in a process called accretion. Dust grains gathered into pebbles, pebbles gathered into boulders, boulders gathered into kilometer-sized bodies called planetesimals, and planetesimals over millions of years gathered into planets. But the disk contained far more solid material than the planets could absorb. For every kilogram of material that ended up in a planet, many more kilograms remained as leftover planetesimals, trillions upon trillions of icy and rocky bodies, ranging from pebble size to the scale of small worlds. These were the raw material not yet incorporated into the growing planets, orbiting in a disk of primordial debris that extended from the inner solar system outward to the edges of the sun's gravitational reach. What happened to those leftover planetesimals is the story of how the Oort Cloud was built, and it is a story that begins with violence. The key to understanding the Oort Cloud's formation lies in a model developed in the early 2000s by a group of planetary scientists working in Nice, France, a model that became known simply as the Nice model, pronounced in the French manner. The scientists were Alessandro Morbidelli, Harold Leveson, Cleomenis, Tsiganis, and Rodney Gomes, and what they proposed overturned decades of assumptions about how the outer solar system reached its current configuration. The standard picture before the Nice model assumed that the giant planets, Jupiter, Saturn, Uranus, and Neptune had formed roughly where they are today and had remained there throughout the solar system's history. The outer solar system was assumed to be approximately stable, its current architecture a direct reflection of its initial state. The Nice model demolished this assumption. What Morbidelli and his colleagues showed, through detailed computer simulations of gravitational interactions between the giant planets and the primordial disk of planetesimals, was that the outer solar system's early history was not stable at all. It was catastrophically unstable. And the instability was not an anomaly or an accident. It was inevitable, a direct consequence of the gravitational dynamics of multiple massive planets orbiting in proximity to a massive disk of smaller bodies. In the Nice model, the giant planets originally formed in a more compact configuration, clustered closer together and closer to the Sun than they are today. Beyond their orbits stretched the primordial planetesimal disk, a vast ring of icy bodies containing perhaps 35 to 50 Earth masses of material, extending from just outside the outermost planet's orbit to several tens of astronomical units from the Sun. For a period estimated at somewhere between 500 million and 600 million years after the solar system formed, this configuration was roughly stable. The planets orbited, the disk orbited. The gravitational interactions were complex but balanced. Then, at some point during this era, Jupiter and Saturn drifted into a specific orbital resonance, a gravitational relationship in which Saturn completed exactly one orbit for every two of Jupiter's orbits. This resonance fundamentally changed the gravitational dynamics of the entire outer solar system. The resonance destabilized the orbits of Uranus and Neptune. The two ice giants, suddenly released from their previously stable orbital configuration, began to migrate outward. They plunged into the planetesimal disk like stones thrown into a shallow lake. The gravitational wake of their passage sent planetesimals scattering in every direction. Some were flung inward, crossing the orbits of the inner planets and bombarding the rocky worlds of the inner solar system. In an episode called The Late Heavy Bombardment, a period roughly 3.9 billion years ago, when the cratering rate on the Moon, Mercury, and presumably Earth spiked dramatically before gradually subsiding as the disk was depleted. Others were flung outward. This is the crucial mechanism. As Neptune and Uranus migrated through the disk, their gravitational influence acted as a cosmic slingshot, accelerating planetesimals onto highly elliptical orbits that carried them to enormous distances from the Sun. Most of these scattered objects reached escape velocity and were lost from the solar system entirely, flung into interstellar space on trajectories they would follow forever, exiled from the system that had formed them. But a significant fraction models suggest somewhere between 1% and a few percent of the scattered population were not moving quite fast enough to escape. They reached enormous distances, thousands, tens of thousands of astronomical units, but remained gravitationally bound to the Sun, falling back toward it on orbits that took millions of years to complete. These were the founding population of the Oort Cloud, but scattered outward onto highly elliptical orbits. They were not yet in the stable configuration the Oort Cloud represents today. Their orbits still brought them back into the planetary region at perihelion, where the giant planets could scatter them again, either ejecting them into interstellar space or sending them back inward for another close encounter. To become permanent members of the Oort Cloud, their orbits needed to be stabilized, their perihelion distances raised high enough that the planets could no longer reach them. This stabilization was provided by two external forces that reached into the distant outer solar system from sources far beyond it. The first was the Sun's birth cluster. The Sun did not form alone. Stars almost never do. They form in clusters, dense groups of hundreds or thousands of young stars born simultaneously from the same collapsing molecular cloud. The Sun almost certainly formed in such a cluster, though the cluster dispersed long ago and the Sun's sibling stars have since scattered across the galaxy. Their original proximity to us now lost in the billions of years of independent orbital motion around the Milky Way's center. But in the solar system's first tens of millions of years, before the cluster dispersed, the Sun was surrounded by a dense population of young stars. Some of these neighbors were close enough, perhaps within a few thousand astronomical units at their nearest, to exert significant gravitational influences on objects scattered to the outer reaches of the nascent solar system. The combined gravitational influence of hundreds of nearby stars in a dense cluster creates a tidal environment far stronger than anything the Sun currently experiences in its relatively isolated position in the galactic disk. For planetesimals scattered onto highly elliptical orbits, with aphelia reaching tens of thousands of astronomical units, the tidal forces of the birth cluster were strong enough to significantly modify their orbits over relatively short timescales, millions rather than billions of years. Specifically, the cluster's tidal forces could raise the perihelion distances of these scattered objects, pushing their closest approach points outward, away from the planetary region, and into a zone where the giant planets could no longer reach them. Once a scattered object's perihelion was raised beyond roughly 40 or 50 astronomical units, Neptune's gravitational influence could no longer significantly affect it. The object was effectively detached from the planetary region, locked into a vast, stable orbit, with a perihelion too distant for further planetary scattering. It had become an Oort Cloud member. This process happened quickly by geological standards, within the first 100 million years of the solar system's existence, while the birth cluster was still dense enough to provide the necessary tidal environment. As the cluster gradually dispersed over tens of millions of years, each star drifting away on its own galactic orbit, the external tidal influence weakened. Objects scattered outward after the cluster had dispersed found themselves in a different environment, one in which the cluster's strong tides were replaced by the weaker but permanent tidal influence of the Milky Way itself. The birth cluster shaped the inner Oort Cloud. The galaxy shaped the outer one. The galactic tide is perhaps the most extraordinary force in the story of the Oort Cloud. It is not a force most people have heard of. It does not appear in popular astronomy discussions with the frequency its importance deserves. But for objects in the outer solar system, it is a dominant influence, the gravitational hand of the entire Milky Way, reaching down to shape the orbits of individual frozen mountains drifting in the darkness beyond the planets. The Milky Way contains roughly 200 to 400 billion stars, along with enormous quantities of interstellar gas, dust, and dark matter, the invisible but gravitationally active material that constitutes roughly 85% of the galaxy's total mass. All of this material is distributed in a disk and halo structure through which the Sun orbits at roughly 514,000 miles per hour, completing one circuit of the galactic center approximately every 225 million years. The combined gravitational influence of all this mass creates a tidal field, a gradient of gravitational force that acts on everything within the galaxy. For objects near the Sun, this tidal field is negligible compared to the Sun's own gravity. Jupiter orbits the Sun, not the galactic center, because the Sun's gravitational pull on Jupiter is billions of times stronger than the galactic tidal force at Jupiter's distance. But in the outer Oort Cloud, the Sun's gravity has weakened enormously. At 50,000 astronomical units, the Sun's gravitational pull on an orbiting object is roughly 2.5 billion times weaker than it is at Earth's distance. The galactic tide, which does not weaken with distance from the Sun because it is generated by the mass distribution of the entire galaxy around the Sun, becomes progressively more competitive. At the outer reaches of the Oort Cloud, the ratio of solar gravity to galactic tidal force narrows to near parity. The galactic tide is strong ecnough to systematically modify the orbits of outer Oort Cloud objects over millions of years, rotating their orbital planes, changing their eccentricities, raising and lowering their perihelion distances in a slow, patient, galaxy-driven oscillation. This oscillation is the primary mechanism by which outer Oort Cloud objects are sent inward as new comets. As the galactic tide slowly reduces the perihelion distance of a particular object, that object's closest approach to the Sun gradually moves inward over millions of years. Eventually, after perhaps 10 or 20 or 50 million years of this slow gravitational pressure, the perihelion drops inside the orbit of Jupiter. The object encounters the giant planet's gravity for the first time. Its trajectory is further modified. It may be sent on a new, shorter period orbit. It may be ejected from the solar system entirely, or it may swing around the Sun in a blazing perihelion passage and become visible from Earth as a new long-period comet. The galactic tide does not act alone. It works in concert with the second major perturbation mechanism, the gravitational influence of passing stars. The Sun moves through the Milky Way's disk, and the disk is populated with stars. Not all of them move in perfect parallel with the Sun. Each star follows its own orbit around the galactic center, and those orbits are not perfectly circular or perfectly coplanar. As a result, stars pass through the Sun's general neighborhood on a continuous basis, each one following its own path through the galactic disk at its own speed and direction. Most of these passages are distant, measured in light years, and their gravitational influence on the Oort Cloud is negligible. But occasionally, a star passes closer. Within a light year, within half a light year, in rare cases, within a few thousand astronomical units of the Sun. When this happens, the gravitational influence of the passing star on the outer Oort cloud is significant, not catastrophic. The passing star does not disrupt the entire cloud or strip away its membership in a single encounter, but measurable. The passing star's gravity tugs at the most loosely bound outer cloud objects, perturbing their orbits, raising or lowering their perihelion distances, sending some of them spiraling inward toward the planetary region and flinging others outward into interstellar space. On average, a star passes within roughly 3 light-years of the Sun approximately every 100,000 years. Closer passages within 1 light-year occur roughly every several 100,000 to 1,000,000 years. These encounters have been happening continuously throughout the solar system's 4.5 billion year lifetime, each one stirring the outer Oort cloud like a spoon dragged slowly through a vast frozen soup. The synergy between the galactic tide and stellar perturbations was first analyzed in detail by astronomers Hans Rieckmann, Mark Fouchard, and their colleagues, whose work in the early 2000s demonstrated that the two mechanisms complement each other in maintaining the steady comet supply. The galactic tide systematically evolves orbital parameters on million-year timescales. Stellar passages inject bursts of random perturbation that can accelerate this process or produce new comet showers from regions of the cloud that the tide alone might not reach efficiently. Together, they ensure a continuous rather than episodic delivery of comets from the cloud to the inner solar system. This synergy also explains a feature of the long-period comet record that had puzzled astronomers for decades. The arrival rate of long-period comets does not vary wildly from century to century, suggesting a relatively steady supply rather than a highly bursty one. A mechanism dominated entirely by rare stellar encounters would produce dramatic showers of comets during close stellar passages, followed by long, quiet periods. A mechanism dominated entirely by the smooth galactic tide would produce a steadier but less variable supply. The combination of both the tide as a background driver, stellar passages as occasional boosters, produces a supply that is broadly steady with modest variations over millions of years. The comets arriving in our sky are the output of a process involving the entire Milky Way galaxy. The galaxy stirs the outer solar system, the outer solar system sends messengers inward, and those messengers arrive in our sky as comets. Every long-period comet is, in a very real sense, a gift from the galaxy. Now we must confront the architecture of the Oort cloud itself, its internal structure, its two primary regions, and the division of properties between them that reflects the different formation environments of the inner and outer solar system's ancient history. Planetary scientists divide the Oort cloud into two broad regions, distinguished by their distance from the Sun, their geometry, and their dynamical properties. The inner region is called the Hills cloud, named after the astronomer Jack Hills, who proposed its existence in 1981. The Hills cloud is thought to begin somewhere between 2,000 and 5,000 astronomical units from the Sun and extend outward to roughly 20,000 astronomical units. Unlike the spherical outer Oort cloud, the Hills cloud is believed to retain a somewhat flattened structure, a thick torus or disk shape concentrated loosely around the plane of the solar system. This geometry reflects the fact that the galactic tidal forces responsible for randomizing orbital inclinations are weaker at the Hills cloud distances than in the outer cloud, and have not had enough time over 4.5 billion years to fully sphericalize the population. The Hills cloud is thought to be far denser than the outer cloud, containing perhaps 5 to 10 times more objects per unit volume. Some models estimate the Hills cloud population at several tens of billions of objects, possibly more. It is the reservoir that feeds the outer Oort cloud's scattered disk, and Hills cloud objects are occasionally perturbed into the outer cloud's population, where galactic tidal forces then take over and redirect them further. The outer Oort cloud begins beyond the Hills cloud, roughly beyond 20,000 astronomical units, and extends outward to somewhere between 50,000 and 100,000 astronomical units, with some estimates placing the absolute outer boundary as far as 150,000 to 200,000 astronomical units from the Sun. This outer shell is approximately spherical. The galactic tide has had sufficient time to randomize the orbital inclinations of its members, spreading them into a roughly uniform distribution across all directions from the Sun. Objects in the outer Oort cloud orbit the Sun in every possible direction. Some orbit in the same direction as the planet's prograde. Others orbit in the opposite direction, retrograde. Some trace nearly circular paths at enormous distances. Others follow highly elliptical trajectories that carry them from the outer cloud's far reaches deep into the inner solar system and back again over millions of years. The total population of the outer Oort cloud is estimated at somewhere between several hundred billion and 1 trillion objects, larger than roughly half a mile across. More generous models push this estimate higher. The combined mass of the entire structure, despite containing this staggering number of individual bodies, is believed to be modest, perhaps a fraction of an Earth mass, to as much as a few Earth masses in total, depending on the model. Recent work favors the lower end of this range. For comparison, Jupiter alone contains 318 Earth masses. Saturn contains 95. Even Uranus, the least massive of the ice giants, weighs in at roughly 14.5 Earth masses. The entire Oort cloud, trillions of objects spread across a sphere, potentially light years in diameter, may be less massive than Uranus. This disparity between volume and mass defines the Oort cloud's most counterintuitive property. It is the largest structure in the solar system by an enormous margin, and it is one of the least massive. The most voluminous component of our cosmic home is also its most tenuous. Then, in the autumn of 2024, something unexpected happened inside a planetarium dome in New York City. The Hayden Planetarium at the American Museum of Natural History was preparing a new show called Encounters in the Milky Way. The show required detailed visualizations of the solar system's outer regions, and the production team had obtained simulation data from David Nesvany, a planetary scientist at the Southwest Research Institute in Boulder, Colorado. Nesvany had spent years developing sophisticated computer models of Oort cloud formation and dynamics, simulating the evolution of hundreds of millions of test particles from the early solar system through 4.5 billion years of gravitational history. His simulations were among the most detailed ever run on the subject. The Hayden production team loaded Nesvany's data into their visualization software and projected it onto the planetarium dome for the first time. Astrophysicist Jackie Faraday, who was present for that projection, noticed something that stopped the room: a spiral. In the three-dimensional visualization of the inner Oort cloud, two distinct arms curved outward from the center, winding away from the Sun's vicinity in a pattern unmistakably reminiscent of a spiral galaxy. Not a faint suggestion, not a statistical tendency that required careful analysis to perceive. A clear, visually striking two-armed spiral structure embedded in the inner Hills cloud region. Nesvany's first assumption was that it was an artifact, a rendering error, a distortion introduced by the coordinate transformation used to display the data on the curved dome surface, a visual trick of the projection geometry. He had worked with this simulation data for years and had never seen or suspected any such structure. It had to be a mistake. He went back to his raw simulation data and looked again. The spiral was there. It was not a rendering artifact. It was not a projection distortion. It was present in the raw three-dimensional Cartesian coordinates of his simulated Oort cloud population, visible only when the data was examined from the right viewing angle and in the right coordinate representation. In the standard analytical framework Nesvany had used throughout his research examining orbital parameters rather than physical positions in three-dimensional space, the structure had been completely invisible. Viewed as positions in physical space from the right perspective, it was unmistakable. Nesvany used NASA's Pleiades supercomputer to run additional simulations, testing whether the spiral persisted under different parameters, different stellar encounter histories, different initial conditions for the giant planet migration, different assumptions about the Sun's birth cluster environment. The spiral appeared in every simulation. It was not sensitive to the specific details of the formation history. It was a robust feature, an inevitable consequence of the physics governing the inner Oort cloud's evolution. The physical explanation turned out to be elegant in the way that the best scientific discoveries are elegant, not complicated, but revealing a simplicity that had been hiding beneath the apparent complexity of the data. Objects in the inner Oort cloud exist in a region where two forces compete for gravitational authority: the Sun's gravity and the galactic tidal force. At these intermediate distances, roughly 1,000 to 10,000 astronomical units from the Sun, the galactic tide is strong enough to significantly affect orbital evolution, but the Sun's gravity still dominates. The interplay between these two forces governs the evolution of orbital parameters through a phenomenon called Kozai-Lidov. Oscillations, a well-understood dynamical mechanism in which the gravitational perturbation of an external force causes cyclic oscillations in an orbit's eccentricity and inclination. The key insight is that Kozai-Lidov oscillations do not act uniformly on all objects. Their rate and character depend on each object's specific orbital parameters: its distance from the Sun, its inclination relative to the galactic plane, its eccentricity. Objects at different distances and inclinations evolve at different rates. This differential evolution, operating over billions of years, systematically organizes the population into a coherent pattern in physical space. The pattern that emerges is the spiral, two arms winding outward from the inner cloud center, oriented roughly perpendicular to the galactic plane, stable over billions of years. The structure formed early in the solar system's history, within the first few 100 million years, and has persisted to the present day, largely undisturbed by the stellar encounters that periodically reshape the outer cloud's population. The discovery was published in February 2025 on the preprint server Argziv and submitted to the Astrophysical Journal. It is a candidate finding not yet independently confirmed through direct observation. Directly detecting the spiral would require identifying and precisely mapping the three-dimensional positions of hundreds of individual Oort cloud objects. No current technology can do this. The Vera C. Rubin Observatory, which recently began its legacy survey of space and time in Chile, may discover dozens of Oort cloud objects through its unprecedented wide-field imaging survey. But Nezvorny himself has noted that dozens would not be sufficient to reveal the spiral pattern. Hundreds of well-characterized objects with precise distance measurements would be needed, and achieving that observational benchmark likely lies decades in the future. Nevertheless, the discovery is significant far beyond its immediate observational implications. It reveals something fundamental about the Oort cloud's nature that had not been suspected. The cloud is not a featureless uniform sphere of randomly distributed objects. It has internal architecture. It has structure shaped not by the Sun and the planets, but by the galaxy itself, by the gravitational field of the Milky Way, acting on individual icy bodies over billions of years. The inner Oort cloud carries the fingerprint of the galaxy, written into the positions of frozen objects drifting in darkness at distances of thousands of astronomical units from the Sun, is a record of the Milky Way's gravitational influence, operating across the entire history of the solar system. The galaxy has been sculpting our outer solar system continuously and invisibly since before the Earth's surface had cooled enough to hold liquid water. The spiral in the Oort cloud is not just a geometric curiosity. It is evidence that the solar system and the Milky Way are not separate entities, the solar system inside, the galaxy outside, with the Oort cloud as the boundary between them. They are interpenetrating, mutually sculpting systems. The galaxy reaches in, the solar system reaches out, and in the space between, trillions of frozen objects trace patterns in their orbits that bear the gravitational signature of both. The Oort cloud is the place where the solar system and the galaxy become indistinguishable from each other. And that indistinguishability has consequences for the most basic question of all. Where does the solar system end? The answer, it turns out, is not a place. It is a process. There is a difference between knowing a number and feeling it. You can read that the Oort cloud extends to 100,000 astronomical units from the Sun and understand the sentence perfectly. The words are clear, the number is specific, the sentence passes without difficulty, and yet the sentence does not land. It slides past the mind the way a statistic about national debt slides past technically comprehended, emotionally weightless. The number is too large for the brain to convert into anything resembling experience. This is not a failure of intelligence. It is a feature of human cognition built by evolution over millions of years. Your ancestors needed to track distances walkable in a day, territories crossable in a season, the gap between a thrown spear and its target. They never needed to process numbers requiring scientific notation. The cognitive hardware for spatial reasoning was calibrated to a world measured in miles, not in astronomical units. When distances exceed a few hundred miles, the mental mapping software begins to approximate. When they reach billions or trillions of miles, it simply stops converting, replacing genuine spatial comprehension with a vague emotional label. Very far. The Oort Cloud operates at distances where that label is not just inadequate, it is actively misleading, because very far implies a kind of distance that is merely inconvenient, a long drive, a long flight, a journey requiring effort, but ultimately achievable. Very far does not imply 30,000 years of continuous travel at the fastest speed any human-made object has ever reached. It does not imply a structure so large that light itself needs more than a year to cross it. It does not imply a territory so vast that the entire history of human civilization would need to repeat itself multiple times during the crossing. To feel the Oort Cloud's scale, you cannot simply hear the numbers. You must build the scale from the ground up, comparison by comparison, until the structure assembles itself in your mind and your old mental model of the solar system breaks apart under the weight of what it was always missing. Start with something so familiar, it requires no introduction. The distance from the Earth to the Sun. 1 astronomical unit, 93 million miles. Light covers this distance in 8 minutes and 20 seconds. If you could drive at highway speeds 60 miles per hour, without stopping, without sleeping, without eating, the trip to the Sun would take approximately 177 years. You would have departed shortly after the American Revolution and still not arrived. That is 1 astronomical unit. Hold it. Neptune, the outermost planet, orbits at 30 astronomical units, 30 times the Earth-Sun distance. Light from the Sun reaches Neptune in about 4 hours and 10 minutes. At highway speed, the drive to Neptune would take roughly 5,300 years. You would have departed before the construction of Stonehenge and still be driving today, still hundreds of years from your destination. This is the outer boundary of the planetary solar system, the place where most people's mental map of the solar system ends, the last named world before the darkness. Now step beyond it. Not into the Oort Cloud yet, just into the intermediate territory that the familiar diagram ignores entirely. The Kuiper belt extends to roughly 50 astronomical units. The heliopause, the plasma boundary that generated those misleading headlines, sits at approximately 120 astronomical units. Sedna's aphelion, its most distant orbital point, lies at roughly 937 astronomical units. These numbers sound large, and by the standards of the planetary solar system, they are. But they are not large by the standards of what comes next. The inner edge of the Hills cloud where the Oort Cloud begins sits at approximately 2,000 astronomical units from the Sun. 2,000 astronomical units. That is 67 times farther from the Sun than Neptune. In raw distance, it equals roughly 186 billion miles. Light from the Sun takes about 11.5 days to arrive. At highway speed, the drive would take 354,000 years. You would need to depart during the Middle Paleolithic era of human prehistory, before Homo sapiens had spread beyond Africa, before the extinction of the Neanderthals, before the invention of written language by a factor of roughly 30, and still be driving today to arrive at the inner threshold of the Oort Cloud. But 2,000 astronomical units is only the threshold, the doorstep, the place where the Oort Cloud begins, not where it ends. The Hills cloud extends outward to perhaps 20,000 astronomical units. At that distance, sunlight needs roughly 4 months to arrive. You are now 667 times farther from the Sun than Neptune. The Sun would still be the brightest object in your sky, a dazzling, star-like point of light clearly outshining everything else in the celestial sphere, but it would provide no warmth you could detect, no illumination you could use. At 20,000 astronomical units, the Sun delivers roughly 400 million times less energy per square meter than it delivers at Earth's distance. A solar panel the size of a football field, oriented perfectly toward the Sun at 20,000 astronomical units, would generate approximately 1/10,000th of a watt. Not enough to power a single LED. Not enough to illuminate a single pixel of a digital screen. The Sun is still there, unmistakable in its brilliance relative to other stars, and it delivers essentially nothing in practical terms. Continue outward. The outer Oort cloud begins beyond 20,000 astronomical units and extends to at least 50,000 and possibly to 100,000 astronomical units. Take the commonly cited outer boundary, 100,000 astronomical units from the Sun. At this distance, you are approximately 1.5 light years from the nearest star in the solar system. Sunlight needs 1.5 years to reach you. The Sun still shines as one of the brightest stars visible from your location, roughly comparable to Sirius as seen from Earth, a brilliant sharp point easily found in the sky by anyone who knew where to look. But that bright point delivers no more heat or illumination to your surroundings than Sirius delivers to Earth, which is to say, effectively nothing. The Sun is still bright. It is simply no longer a sun. It is a star, one brilliant point among many, offering light you can see but never feel. And you are still inside the solar system, held in a vast, slow, million-year orbit by a gravitational thread stretched to near transparency across 1.5 light years of vacuum. 1.5 light years. Proxima Centauri, the nearest known star to the Sun, lies at approximately 4.25 light years from us. If the Oort cloud's outer edge sits at 1.5 light years, then the Sun's domain extends more than 1/3 of the way to the nearest neighboring star. Some estimates push the outer boundary to 2 or even 3 light years, which would mean the solar system might reach halfway to Proxima Centauri, possibly further. The space between our Sun and its closest stellar neighbor is not empty interstellar void from edge to edge. A significant fraction of that gap may still belong to our solar system, filled with trillions of icy bodies tracing vast orbits in frozen darkness. The gap between stars is not a gap at all. It is contested territory, overlapping gravitational spheres of influence from neighboring stars, each one extending outward until it dissolves into the galaxy's wider tidal field. This is the point where most people's intuition fails entirely. The solar system extending 1/3 of the way to the nearest star does not compute. It violates the mental model so thoroughly that the brain tends to reject it or reclassify it as exaggeration. It is not exaggeration. It is the direct consequence of the Sun's gravitational reach, which extends far beyond the region where sunlight can warm anything, far beyond the region where the solar wind can blow, far beyond any boundary that feels intuitively like an edge. To make this scale truly concrete, step away from distances for a moment and think about time. NASA's Voyager 1 spacecraft was launched on the 5th of September 1977. It has been traveling continuously ever since, flying outward from the Sun at roughly 38,000 miles per hour, approximately 3.6 astronomical units per year. As of 2026, Voyager 1 is approximately 165 astronomical units from the Sun. It has been traveling for nearly 49 years. In those 49 years, it has covered 165 astronomical units. The inner edge of the Oort cloud sits at roughly 2,000 astronomical units. At Voyager's current speed, it will reach the inner edge of the Oort cloud in approximately 300 years. Not 300 years from its launch, 300 years from now, in the mid-2300s, Voyager 1 will finally begin to enter the structure whose existence helps define the true extent of the solar system. But entering the Oort cloud is not the same as crossing it. The inner edge begins at 2,000 astronomical units. The outer edge sits at 100,000. At Voyager's current speed of 3.6 astronomical units per year, Crossing the full radial extent of the Oort Cloud from inner edge to outer boundary would take approximately 27,000 years. Add the 300 years to reach the inner edge. The total time from Voyager's 1977 launch to its exit from the outer Oort Cloud is approximately 30,000 years. 30,000 years. When Voyager 1 finally exits the Oort Cloud and enters true interstellar space, the region where the Sun's gravitational dominion has dissolved entirely, the following things will have happened on Earth since its launch. Every human civilization currently existing will have risen, transformed beyond recognition, and most likely ended. Every language currently spoken will have evolved into something mutually unintelligible with its present form, or gone extinct entirely. The coastlines of continents will have shifted measurably from today's positions. Species currently alive will have evolved or gone extinct. Ice ages may have come and gone. And the entire span of recorded human history, from the earliest Sumerian writing tablets to whatever civilization exists in 30 millennia, will have elapsed once over during Voyager's crossing of a single solar system structure. Not a crossing of the galaxy, not a journey to another star. The crossing of our own solar system's outermost region. This is the structure surrounding you right now. Now build a physical model. Science teachers around the world have been building scale models of the solar system with their students for generations. You place a basketball on one end of a schoolyard to represent the Sun. Mercury is a small pebble a few paces away. Earth is a marble at the distance of about 30 feet. Jupiter, a golf ball, sits roughly 150 feet from the basketball. Neptune, a small bead, is placed about half a mile away. The model is extraordinary. Students walk its length and feel the emptiness between worlds, the vast spaces that the flat diagram compresses into meaninglessness. And then the lesson ends. The students walk back to the classroom. The teacher claps the chalk dust from their hands. The model stops at Neptune. It always stops at Neptune. Every scale model solar system ever built for educational purposes ends at Neptune, or perhaps at Pluto, because extending the model to include the Oort Cloud would be physically impossible within the boundaries of any school, any campus, any city. Here is the arithmetic. In a model where the basketball sun sits at one end of the schoolyard and Neptune, the small bead is placed half a mile away, the inner edge of the Oort Cloud would need to be located roughly 33 miles from the basketball. That is already outside most metropolitan areas. The model has left the city before it has even reached the beginning of the structure it needs to represent. The outer edge of the Oort Cloud at 100,000 astronomical units would need to be placed approximately 1,650 miles from the basketball sun. In the United States, that is the distance from New York City to Denver. In Europe, it is the distance from London to Moscow. The scale model that fit comfortably in a schoolyard for the planets would need to stretch across half a continent to include the Oort Cloud. The basketball sits on the sidewalk in front of your school. Neptune is a bead somewhere across town. The inner Oort Cloud begins in a neighboring state, and the outer boundary of the solar system is in a different time zone. Every schoolyard model ever built has been teaching children the same truncated lesson, showing them the lit core and cutting off the picture before it reveals its true dimensions, not through deception, through the simple physical impossibility of representing the real scale on a surface small enough for human beings to stand beside. Volume makes the disparity even more visceral. Volume scales with the cube of the radius. If the Oort Cloud's outer boundary is roughly 3,300 times farther from the Sun than Neptune's orbit, then the volume of the sphere enclosed by the Oort Cloud's outer boundary is approximately 36 billion times larger than the volume of the sphere enclosing the planetary solar system. 36 billion times. Every planet, every moon, every asteroid, every Kuiper Belt object, every spacecraft humanity has ever launched, all of it resides within a volume so small relative to the full solar system that expressing the ratio requires the kind of numbers that lose all human meaning on contact. Try this instead. Imagine the Oort Cloud as a sphere the size of the Earth, a perfect globe 8,000 miles in diameter, representing the full extent of the Sun's gravitational domain. At this scale, the planetary solar system, everything from Mercury's orbit to Neptune's, would be a sphere roughly 4 kilometers across at the center of that Earth-sized globe. A small hill town swallowed inside an entire world. All 8 planets, all their moons, the asteroid belt, the Kuiper belt, the heliopause, every photograph ever taken by every spacecraft, every human achievement in space exploration. All of it fits inside a region that, relative to the Oort Cloud, is smaller than a village compared to the entire globe. Now return to the classroom diagram one more time. That neat row of planets stretching from Mercury to Neptune, the image you have carried since childhood, represents a region of space so tiny relative to the actual solar system that rendering both to accurate scale in a single image is not merely difficult, it is impossible. If you drew the Oort Cloud as a circle the size of a classroom wall, the planetary solar system at its center would be smaller than the period at the end of this sentence. Not a small dot, a period, the full stop, the smallest mark a printer can make. That period contains everything. Every planet, every moon, every spacecraft, every place a human being has ever pointed a camera, reduced to a punctuation mark inside a structure that fills the entire wall. Now confront the paradox at the heart of this structure. The Oort Cloud contains, by conservative estimate, several hundred billion objects. By more generous models, 1 trillion or more. Each one a frozen body, a mountain of ancient ice and rock, a preserved fragment of the primordial solar system, an object that has existed in near unchanged form since before the first complex life appeared on Earth. 1 trillion objects sounds crowded. It sounds like a dense swarm, a thick fog of debris filling the space around the Sun, a tangible cloud you could fly through and feel closing in around you. It sounds like a place with texture, with presence, with the physical sensation of occupying populated space. The reality is the precise opposite. The volume the Oort Cloud occupies is so incomprehensibly vast that 1 trillion objects vanish inside it, like individual grains of sand cast into the Pacific Ocean. Consider the arithmetic. If the outer Oort Cloud contains roughly 1 trillion objects distributed throughout a spherical shell between 20,000 and 100,000 astronomical units, the average distance between any 2 neighboring objects is on the order of tens of billions of miles, roughly 10 to 30 times the distance from the Earth to the Sun. The nearest neighbor to any given Oort Cloud object is, on average, as far away as the gap between the Sun and Saturn. That is not a crowded environment. That is a void, punctuated by the occasional frozen mountain, separated from its nearest companion by a gulf that would take our fastest spacecraft years to cross. An observer sitting on one Oort Cloud body, looking in every direction, would see nothing. No nearby companions catching faint starlight, no surfaces glinting in the pale glow of a distant sun, no sense whatsoever of belonging to a population, just stars and darkness, indistinguishable from any other patch of deep space. This sparsity is so extreme that 2 neighboring Oort Cloud objects, drifting through their multi-million-year orbits, could theoretically drift for the entire age of the solar system, 4.5 billion years, without ever coming close enough to each other to experience a measurable gravitational interaction. They share a solar system. They may have formed within the same region of the primordial disk, and they will never meet. The Oort Cloud is a museum where every exhibit is separated from every other exhibit by billions of miles of vacuum, and no visitor has ever walked its halls. This sparsity resolves another counterintuitive fact about the Oort Cloud. Despite containing perhaps 1 trillion or more individual objects, its total mass is startlingly modest. Current estimates, informed by models of planetary formation and comet supply dynamics, place the outer Oort Cloud's total mass at somewhere between a fraction of an Earth mass and perhaps a few Earth masses. Recent work, including a 2025 paper by Simon Porteghese-Zwart and colleagues, favors the lower end of this range, a few Earth masses. At most, Jupiter alone contains 318 Earth masses. Saturn contains 95. Uranus, the least massive giant planet, contains roughly 14.5. The entire Oort Cloud, that trillion-object, light-year-spanning sphere, may weigh less than Uranus. It may weigh less than a single ice giant that you can see with the naked eye on a clear night. The most voluminous structure in the solar system, one of the least massive. This seems impossible. It seems like a contradiction. How can a structure containing 1 trillion objects weigh less than a single planet? The answer lies entirely in the object's sizes. Most Oort Cloud members are not large. The typical Oort Cloud body is estimated to be a few miles across, smaller than a city, comparable in size to a mountain. 1 trillion mountains spread across a sphere, 1.5 light-years in radius, produces a total mass that is, cosmically speaking, trivial. Compare this to Earth, whose radius is roughly 4,000 miles. The Earth is not 1 trillion mountains. It is a solid sphere of compressed rock and metal, dense and continuous. The Oort Cloud is the opposite, an enormous volume containing an enormous number of small, isolated, sparse objects, separated by distances that make meaningful interaction between them essentially impossible. The Oort Cloud is not a cloud in any visual sense. It does not look like a cloud. It does not feel like a cloud. It is a statistical population, a description of where things are, not a substance you could touch or see or measure with any instrument aboard any spacecraft that currently exists. If you flew through the Oort Cloud in a spacecraft, you would have no sensory evidence of its existence, no thickening of surrounding material, no increased frequency of particle impacts on your hull, no change in the starfield outside your window, no gravitational anomaly registering on your instruments. You could cross the entire radial extent of the Oort Cloud, from inner edge to outer boundary, 30,000 years of travel at Voyager's speed, and never once encounter a detectable object. Never once have any reason to believe you are inside a structure at all. The Oort Cloud is there. It is confirmed by every line of evidence that comet science and orbital mechanics can bring to bear, and it is simultaneously nothing, a ghost written in gravity and statistics rather than in matter, dense enough to see or touch. A structure known entirely through its consequences, through the comets it releases, not through any physical presence it possesses. 1 trillion objects rendered collectively invisible by the sheer volume they inhabit. This is the paradox at the heart of the solar system's largest structure, everywhere and nowhere, real and imperceptible. The most populated region of the solar system and the most desolate, 1 trillion frozen mountains drifting in a darkness so complete, a silence so absolute, a cold so profound that no human language developed on a warm, noisy, sunlit planet has adequate words for what it would mean to be there. And all of it, every frozen object in that vast dark sphere, belongs to the same star that warms your skin on a summer afternoon. The same star, 1.5 light-years away. Every map humanity has ever drawn required an edge, the coastline of a continent, the border of a nation, the property line of a yard. Maps work because they have boundaries, clean lines separating what belongs inside from what belongs outside. The human mind craves these boundaries. It organizes reality by sorting things into containers with defined limits. This is my house. That is the street. Beyond the street is the neighbor's property. The world makes sense because the categories have edges. The solar system was supposed to have an edge. For centuries, that edge was implicit in every diagram, every model, every description of our cosmic neighborhood. The planets orbit the sun. Beyond the last planet, the solar system ends. Interstellar space begins. A clean line, a clear boundary. Inside is home, outside is the void. The human mind could hold this structure because it behaved like every other bounded space in human experience. The Oort Cloud does not merely push that edge outward to a new, farther location where a clean line can be redrawn. It does not blur the boundary slightly or complicate it modestly. It eliminates the concept of a boundary entirely. The solar system does not end, it fades. And the region across which it fades is so vast, so gradual, and so interpenetrated with the forces of the wider galaxy that no line can be drawn anywhere along its length without being arbitrary in a way that strips the line of any real meaning. To understand why, you need to look at what happens at the Oort Cloud's outermost reaches, the region where the Sun's gravitational authority begins to dissolve. Not into nothing, the Sun's gravity never reaches zero, but into something so weak, so contested, so overwhelmed by competing forces from the wider galaxy that the word ownership loses its meaning. At the center of the solar system, the Sun's gravity is overwhelming. Mercury orbits at 36 million miles, completing a loop every 88 days, moving at roughly 107,000 miles per hour. The Sun's grip on Mercury is so strong that Mercury's escape velocity, the speed needed to break free from the Sun at that distance, exceeds 130 miles per second. Moving outward, that grip weakens. Neptune, at roughly 2.8 billion miles from the Sun, moves at only 12,100 miles per hour in its orbit. The Sun still holds it firmly, but the leash is longer and the pace is slower. The orbital velocity of any bound object decreases with distance, following the mathematics of gravitational mechanics precisely. In the Oort Cloud, the leash becomes gossamer. At 50,000 astronomical units, an object bound to the Sun moves at a speed so small it borders on the incomprehensible, roughly 1/5 of a mile per hour, a slow walking pace. A healthy adult human could outpace this object's orbital velocity, and yet that object is traveling fast enough relative to the Sun at that distance to remain in orbit, tracing an enormous ellipse that takes millions of years to complete, creeping along its path at a pace that would be imperceptible over any timescale accessible to human observation. The Sun's gravitational pull at 50,000 astronomical units is real. It is not zero. But it is so weak that other forces operating across the solar system's outer reaches begin to compete with it on nearly equal terms. And the most important of those competing forces is one we have already encountered: the galactic tide. The Milky Way's gravitational field acts on everything within the galaxy, including the outermost objects orbiting our Sun. For the planets, the galactic tide is negligible, overwhelmed by the Sun's dominant pull by factors of billions. But as distance from the Sun increases and the Sun's gravity weakens accordingly, the galactic tide's relative influence grows. At some critical distance, the point where the Sun's gravitational pull on an orbiting object exactly equals the galaxy's tidal force pulling in the opposite direction, stable orbits become impossible. This boundary is called the Hill sphere, named after the American astronomer George William Hill, who developed the mathematical framework for understanding gravitational spheres of influence in the late 19th century. The Hill sphere defines the region around any astronomical body within which its gravity dominates over the tidal forces of the larger system it orbits. For the Sun, orbiting the center of the Milky Way at a distance of roughly 26,000 light-years, the Hill sphere has a radius of approximately 1 to 2 light-years. Read that carefully. The Sun's Hill sphere, the region within which its gravity can maintain stable bound orbits against the galactic tide, extends to 1 to 2 light-years. The commonly cited outer boundary of the Oort Cloud sits at 1 to 1.5 light-years. This is not a coincidence. The Oort Cloud extends as far as the Sun's gravitational authority allows, and no farther. Its outer edge is defined not by any intrinsic property of the cloud itself, but by the point at which the galaxy takes over. The Oort Cloud fills its gravitational container precisely to the brim, but this transition from solar dominance to galactic dominance is not a wall, it is not a line, it is a gradient. There is no distance at which the Sun's gravity suddenly drops to zero and the galaxy's tidal force suddenly activates. Both forces operate continuously at every distance. What changes is their ratio. Close to the Sun, solar gravity overwhelms the galactic tide by factors of billions. In the outer Oort Cloud, the two forces approach rough parity. Beyond the Hill sphere's outer limit, the galaxy wins. The outer edge of the solar system is not a boundary in any physical sense. It is a probability distribution. The fraction of objects that are gravitationally bound to the Sun decreases gradually with distance from nearly all at the inner cloud to essentially none where the galactic tide has swept everything away. There is no point where you cross from inside to outside. There is only a vast transitional region where belonging to the solar system becomes progressively less certain, less stable, less meaningful. An object at the Oort Cloud's outer edge does not know it is in the solar system. It has no awareness of the Sun as anything special. The Sun is a distant star, one of many, exerting a gravitational pull barely distinguishable from the combined pull of everything else in the galactic neighborhood. The object's orbit is not a clean ellipse. It is a wobbling, precessing, chaotically perturbed trajectory that may remain bound to the Sun for another billion years, or may be dislodged by the next passing star and sent drifting into interstellar space. Its allegiance to the solar system is provisional, temporary, a gravitational accident that could be undone by any sufficiently close encounter. Close encounters are not rare. The Sun moves through the Milky Way's disk at roughly 514,000 miles per hour, orbiting the galactic center along a path shared by hundreds of billions of other stars, each following its own trajectory through the galaxy. These trajectories are not perfectly parallel. They cross, they converge and diverge over millions of years as each star responds to the gravitational influences of its neighbors and the broader galactic field. And occasionally, two stars pass close enough for their gravitational fields to interact meaningfully with each other's outermost regions. On average, a star passes within roughly 3 light-years of the Sun every 100,000 years. Most of these passages are too distant to significantly perturb the Oort Cloud. Their gravitational influence at 3 light-years barely registers against the Sun's own field at comparable distances, but closer passages occur. Within 1 light-year, perhaps once every several 100,000 to a million years. Within half a light-year, less frequently still, and occasionally over the solar system's 4.5 billion-year history, a star has passed close enough to reach deep into the Oort Cloud's populated regions. Each such passage stirs the cloud, some outer cloud objects, their orbits gently shifted by the passing star's gravity, find their perihelion distances lowered, their closest approaches to the Sun pushed inward. Over the following millions of years, some of these nudged objects will fall inward far enough to enter the inner solar system as new long-period comets. Others will be flung outward entirely, escaping the Sun's weakened grip and entering interstellar space as permanent exiles. The most dramatic upcoming encounter that astronomers have identified in current stellar catalogues involves a star designated Gliese 710. Gliese 710 is an orange dwarf star, smaller and cooler than the Sun, roughly 60% of the Sun's mass, currently located approximately 64 light-years away in the constellation Serpens. Under ordinary circumstances, it would be an unremarkable background star, invisible to the naked eye and attracting no special attention from solar system scientists. But measurements from the European Space Agency's Gaia spacecraft, which has been mapping the positions and velocities of over 1 billion stars with unprecedented precision, revealed something extraordinary about Gliese 710's trajectory. It is heading almost directly toward us. In approximately 1.3 million years, Gliese 710 will reach its closest approach to the Sun. Based on current Gaia measurements, that closest approach is estimated at roughly 10,000 to 13,000 astronomical units, well within the denser Hills cloud region of the inner Oort Cloud. Some orbital solutions, accounting for uncertainties in the current measurements, allow for an approach as close as several thousand astronomical units. At 10,000 astronomical units, Gliese 710's gravitational influence on the Oort Cloud will be significant. Not catastrophic in the sense of destroying the solar system or disrupting the planetary orbits. The inner solar system will be entirely unaffected by a star passing at 10,000 astronomical units. But for objects in the Hills cloud and the outer Oort Cloud, whose orbital binding energies are small and whose trajectories are easily perturbed, Gliese 710's passage will be a major gravitational event. Models of the encounter suggest it could dislodge millions or even billions of Oort Cloud objects from their current orbits. Some will be accelerated into interstellar trajectories. Others will have their perihelia lowered enough to begin falling toward the inner solar system. Over the several million years following the encounter, Earth's sky may experience a dramatic increase in long-period comet arrivals, a comet shower, in the technical astronomical sense, as the objects displaced by Gliese 710's passage reach the inner solar system one after another. This event is not a threat in any civilizational sense. The comets will arrive gradually over millions of years, not simultaneously. The probability of any single comet striking Earth during such a shower is extremely small. But the event is a reminder that the Oort Cloud is not a sealed vault, insulated from the galaxy around it. It is an open system, continuously sculpted by encounters with the stellar neighborhood through which the sun perpetually moves. The solar system is not isolated. It never has been. The most direct evidence that the solar system is an open system, that its boundaries are permeable, and that matter crosses them in both directions, continuously arrived in our sky, not as a comet, but as something stranger, something that had never been seen before in the entire history of astronomical observation. On the 19th of October 2017, astronomers at the Haleakala Observatory in Hawaii, using the PAN, Stars 1 telescope, as part of a routine sky survey, detected an object moving through the inner solar system on a trajectory that defied every expectation of what a solar system object could do. Its orbit was hyperbolic. A hyperbolic orbit means the object is moving faster than the sun's escape velocity at its current location. It is not bound to the sun. It will pass through the solar system once, swing around the sun, and depart on a trajectory that will carry it out of the solar system forever, never to return. Objects with hyperbolic orbits exist in theory. The giant planets can occasionally fling smaller bodies onto hyperbolic trajectories, sending them out of the solar system. But those objects arrive at hyperbolic velocities because they were accelerated within the solar system. What Pan-STARRS had found was different. The excess velocity of this object, the amount by which its speed exceeded the sun's escape velocity, was too large to be explained by any acceleration occurring within the solar system. The object had arrived at the solar system's outer edge, already moving too fast to be gravitationally captured. It had come from outside, from interstellar space, from another star system, traveling through the void between stars for an unknown duration before entering our solar system's gravitational environment. It was named Oumuamua, a Hawaiian word meaning scout or messenger from afar arriving first. Oumuamua was extraordinary in several respects. It was the first confirmed interstellar object ever detected passing through our solar system. Its shape, inferred from the way its brightness varied as it rotated, was unusually elongated, possibly 10 times longer than it was wide, a geometry unlike any solar system object ever catalogued. It showed no detectable coma or tail when it approached the sun, suggesting it was not a comet in the conventional sense. And as it departed the inner solar system, its acceleration slightly exceeded what gravity alone could explain. The cause of that excess acceleration has been debated extensively. Outgassing from volatile ices, hydrogen ice, perhaps, or some other substance that would not produce a visible coma, remains the leading scientific explanation. The hypothesis attracted both serious scientific analysis and considerable public speculation. What is not in dispute is the object's interstellar origin, confirmed by multiple independent analyses of its orbital trajectory. Oumuamua came from another star. It passed through our solar system, and it left. 2 years later, in August 2019, a Crimean amateur astronomer named Gennady Borisov was conducting an independent sky survey using a telescope he had built himself. He discovered a new comet. Its trajectory was calculated, and within days, astronomers realized they were looking at a second interstellar visitor, Comet 2I. Borisov was unambiguously a comet. Unlike Oumuamua, it displayed a clear, fully developed coma and tail, the signature of volatile ices sublimating under the sun's heat. Its composition was analyzed in detail. Water, carbon monoxide, nickel, and several organic compounds were detected in its coma. Its chemistry was broadly similar to solar system comets, suggesting that the processes of comet formation in the early solar system accretion of icy planetesimals from a protoplanetary disk operate similarly around other stars. Borisov was, in the most literal sense, a piece of another star's Oort Cloud, an icy body that had formed in the protoplanetary disk of a distant sun, been scattered outward into that system's equivalent of our outer solar system, and eventually been perturbed into an interstellar trajectory, perhaps by a stellar encounter in its home system, perhaps by its own star's galactic tidal forces. It had then traveled through interstellar space for an unknown period, perhaps millions or billions of years, before chance carried it through the gravitational territory of our Sun. It was a fragment of a foreign solar system, and for a few months in late 2019, it was close enough to Earth to analyze with ground-based telescopes. Oumuamua and Borisov are not isolated curiosities. They are harbingers of a recognition that has been building in the astronomical community for years, and that transforms the conceptual framework within which the Oort Cloud must be understood. The galaxy is not a collection of isolated stellar systems separated by empty interstellar voids. It is a connected system in which material flows continuously between stars, carried by objects ejected from planetary systems through the same mechanisms that built our Oort Cloud giant planet scattering, galactic tidal perturbations, stellar encounters. Every star that has ever formed with planets or planetesimals has, with high probability, ejected large quantities of material into interstellar space during its early history. The NICE model predicts that our own solar system ejected roughly 90 to 99% of the primordial planetesimal disk into interstellar space during the giant planet migration era. Other solar systems almost certainly did the same. The interstellar medium is therefore populated not just by gas and dust, but by a continuous, galaxy-wide rain of icy and rocky bodies ejected from countless planetary systems, a diffuse background population of interstellar wanderers drifting through the spaces between stars on trajectories shaped by the cumulative, gravitational influences of every system they have passed through. Statistical models of the detection rates of Oumuamua and Borisov suggest that at any given moment, thousands of interstellar objects larger than 100 meters in diameter are passing through the volume of space inside Neptune's orbit. The solar system is being continuously traversed by material from other stars, and our solar system is continuously ejecting material into the same interstellar flow. The Oort Cloud is both the source and the sink of this exchange. Objects perturbed from the outer Oort Cloud by stellar encounters or galactic tidal forces join the interstellar population. Objects from other stars' Oort Cloud equivalents occasionally enter our solar system's gravitational domain, and if their approach is slow enough relative to the Sun, may even be temporarily captured into bound orbits, becoming, for a period, members of our own outer solar system. This means the Oort Cloud may already contain objects that did not form around our Sun. During the solar system's early history, when the Sun was still embedded in its birth cluster alongside hundreds of sibling stars, the gravitational environment was dense enough for material to be exchanged between neighboring systems directly. Objects scattered outward from one star's protoplanetary disk could have been captured by a neighboring star's gravity and incorporated into that star's forming Oort Cloud. Simulations of this process, conducted by Simon Porteous-Zwart and colleagues, suggest that a meaningful fraction, possibly several percent of the Oort Cloud's current population may consist of objects that originally formed around other stars. Objects captured during the chaotic, crowded early years of the Sun's existence before the birth cluster dispersed and the Sun settled into its current relative isolation. Our solar system's outermost structure is not entirely ours. It is a mixture, a blend of local material and imported debris, assembled from the raw material of our own protoplanetary disk and supplemented over billions of years by captures from the interstellar flow. The Oort Cloud's membership is cosmopolitan in a way that no other solar system structure is. The boundary between our solar system and the rest of the galaxy was breached at the very beginning. It has never been sealed since. Now stand at the outer edge of the Oort Cloud and look both ways. Inward, toward the Sun, 1.5 light years of dark, cold, nearly empty space, populated by trillions of frozen objects in ancient orbits, growing gradually denser as you approach the Hills Cloud and then the scattered disk and then the Kuiper Belt and finally the bright, warm, bustling inner solar system with its 8 planets and their moons and the thin blue atmosphere of one small world where complex chemistry has somehow, against every expectation of probability, organized itself into awareness. Outward toward the stars, the interstellar medium, the void between suns, not empty, populated by gas and dust and the occasional wandering interstellar object, traversed by the light of distant stars and the faint glow of the cosmic microwave background, and at approximately 2.5 to 3 light-years in the direction of the southern sky, the outer reaches of Proxima Centauri's gravitational domain. Proxima Centauri sits at 4.24 light-years from the Sun. If the Oort Cloud's outer edge sits at 1.5 light-years, and Proxima Centauri's equivalent outer cloud reaches inward by a comparable distance, then the gap between the two clouds, the true no man's land between stellar systems, may be as little as 1 to 2 light-years across. A year or two of light travel time separating the outermost influence of our Sun from the outermost influence of the nearest neighboring star. The space between stars is not a vast, uniform desert with isolated planetary oases scattered through it. Each star sits at the center of an enormous gravitational domain, its territory extending outward until it meets the territory of its neighbors. The interstellar medium is partitioned into overlapping, gradually fading spheres of gravitational influence, each one defined by an outer shell of icy debris, tracing ancient orbits around a distant point of light. You do not leave one solar system and then travel through empty void before arriving at another. You leave one star's fading grip and almost immediately begin to feel the growing influence of the next. The galaxy is not a collection of isolated stars. It is a mosaic of overlapping gravitational territories, each one blending at its edges into the territories of its neighbors, the boundaries between them defined not by walls, but by the gradients where one star's dominance yields to another's. In this picture, the solar system is not a sealed container surrounded by void. It is an open territory, a gravitational sphere of influence that reaches into space until the galaxy takes it back, continuously exchanging material with the interstellar environment, perturbed and sculpted by every stellar encounter and every cycle of the galactic tide. The Oort Cloud is not the edge of the solar system. It is the membrane through which the solar system breathes. And the solar system has been breathing in and out for 4.5 billion years, exhaling comets and planetesimals into interstellar space, inhaling visitors from other stars, its outermost boundary forever dissolving into the galaxy rather than ending against it. There is one more consequence of this openness that deserves to be named directly because it alters the meaning of the solar system's history in a way that nothing else quite does. If the Oort Cloud contains material from other stars' objects captured during the birth cluster era, supplemented over billions of years by occasional interstellar captures, then some of the frozen bodies currently orbiting our Sun in the outer Oort Cloud formed around stars that no longer exist. Stars that burned brighter and hotter than the Sun, lived shorter lives, and ended in supernovae before the Earth's crust had solidified. Stars whose planetary systems we will never identify, whose locations in the modern galaxy we cannot determine, whose histories are entirely unknown to us. Their material is here, orbiting our Sun in frozen silence at distances of tens of thousands of astronomical units, incorporated into the same vast dark sphere that surrounds our solar system, indistinguishable from the objects that formed in our own protoplanetary disk. The Oort Cloud is an archive, an ancient repository of material from the solar system's birth, supplemented by contributions from stellar neighbors across billions of years of galactic history. It contains some of the oldest and most pristine solid matter in the solar system, and some of that matter may be even older than the Sun preserved from planetary systems that formed and were destroyed before our own star ignited. When a long-period comet arrives in our sky for the first time, blazing briefly as its ancient ices sublimate under the Sun's heat, we are not just witnessing a beautiful spectacle. We are watching the delivery of an ancient message from a reservoir that may contain records stretching back to before the solar system existed. The comets are the Oort Cloud's voice, and the Oort Cloud, it turns out, has been listening to the entire galaxy. That voice carries stories older than Earth, stories written in ice and preserved in darkness at temperatures just above absolute zero, waiting for the right gravitational nudge to send them falling inward toward the one warm, a lit corner of this vast frozen sphere where something exists that is capable of reading them. That something is us. And what we have learned from reading those messages, from tracing the trajectories of ancient comets back to their origins, from mapping the structure of a cloud we have never seen, from inferring the galaxy's fingerprint in the orbital patterns of frozen mountains drifting in the dark, what we have learned is the subject of the final reckoning. The reckoning with what the Oort Cloud means, not just for the solar system's size, but for what it means to live inside a home this large, this dark, this ancient, and this open to the universe beyond it. You began this journey with a diagram. A bright yellow sun at the center, 8 planets arranged in neat concentric rings, Mercury close and grey, Earth blue and small, Jupiter banded and enormous, Neptune at the outer edge, a deep cold blue, the last named world before the darkness. The diagram ended there. The solar system was finished, clean, orderly, comprehensible. A structure that fit on a poster, fit in a classroom, fit inside the mental model you carried since childhood without ever straining its edges. That diagram is still accurate. Every planet in it is real. Every orbit is precisely measured. The distances between worlds follow the laws of physics with a fidelity that has allowed us to send spacecraft to the outer planets and thread them through gravitational slingshots calculated to within fractions of a degree. The diagram is not wrong, but you now know what it leaves out. Beyond Neptune's orbit at 30 astronomical units stretches the Kuiper belt, extending to 50. Beyond that, the scattered disk, populated by objects flung into extreme elliptical orbits by the gravitational upheaval of the solar system's early history. Beyond that, the heliopause at 120 astronomical units, the plasma boundary that generated global headlines in 2012 when Voyager 1 crossed it, the boundary mistaken by millions for the solar system's edge. Beyond that, in the dark intermediate territory where Sedna drifts on its 11,400-year orbit, carrying the gravitational fingerprints of forces no known planet can explain, the territory between the known solar system and the structure that defines the true extent of the Sun's domain, and then, beginning at roughly 2,000 astronomical units, and extending outward to perhaps 100,000 to 1.5 light-years from the Sun, the Oort Cloud. The structure that contains everything else within it the way an ocean contains a candle flame. Let the numbers speak one final time, stripped of context, arranged in sequence, so their cumulative weight can settle completely. Neptune orbits at 30 astronomical units. The Oort Cloud's inner edge begins at 2,000. The outer boundary sits at 100,000. The entire planetary solar system, every world, every moon, every asteroid, every spacecraft humanity has ever launched, occupies the innermost 0.03% of the solar system's true radial extent. The Oort Cloud constitutes more than 99.97% of the distance from the Sun to the solar system's outer boundary. By volume, the disparity is even more extreme. The sphere enclosed by the Oort Cloud's outer boundary is roughly 36 billion times larger than the sphere enclosing the planetary solar system. The planets, moons, and all of human space exploration occupy a fraction of the total solar system volume so small that no classroom poster, no documentary animation, no diagram of any kind can represent both structures at accurate scale simultaneously. If you drew the Oort Cloud as a circle the size of a wall, the planetary solar system at its center would be smaller than a period on a printed page. Voyager 1, after nearly 49 years of continuous travel at 38,000 miles per hour, has covered less than 0.2% of the distance to the Oort Cloud's outer edge. At its current speed, it will not exit the solar system, the real solar system, the full gravitational domain of the Sun, for approximately 30,000 years. The Oort Cloud contains, by conservative estimate, several 100 billion objects. By generous models, 1 trillion or more. Their combined mass is less than a few Earth masses, less than the mass of a single ice giant planet. They drift in absolute darkness at temperatures approaching absolute zero, separated from their nearest neighbors by distances comparable to the gap between the Earth and Saturn, invisible to every telescope humanity has ever built, detectable only through the comets they occasionally release, each one a frozen message from a reservoir we have never seen. The galactic tide of the Milky Way sculpts the orbits of objects in the outer Oort Cloud continuously, rotating their orbital planes over millions of years, lowering their perihelion distances until they fall inward as new long-period comets. Supercomputer simulations revealed in 2025 that the inner Oort Cloud possesses a two-armed spiral structure, generated by the differential action of galactic tidal forces on objects at different distances and inclinations, the fingerprint of the Milky Way written into the architecture of our own outer solar system. Interstellar visitors have been detected passing through the inner solar system, confirming that the Oort Cloud is not a sealed vault, but an open membrane through which the solar system exchanges material with the wider galaxy. The solar system's outer boundary is not a wall, it is a gradient. The region where the sun's gravitational authority fades into the galaxy's tidal dominance over distances measured in light years, with no clean line separating inside from outside, belonging from not belonging, home from the void. These are not speculations. They are the conclusions of orbital mechanics, comet science, galactic dynamics, and planetary formation, modeling the cumulative work of generations of astronomers, building on the foundational insight of Jan Oort, who sat with 19 comet trajectories in 1950 and inferred from their mathematics a structure that humanity will not directly observe for centuries, if ever. Now, consider what this means for the word home. When most people say they live in the solar system, they imagine a compact, sunlit neighborhood, 8 planets, orbiting a warm star, surrounded by empty darkness, a bounded and knowable place. The solar system of the classroom poster. The solar system that fits in a diagram. The Oort Cloud reveals that this picture is not wrong so much as it is radically, almost comically incomplete. Home is not the lit stage at the center of the diagram. Home is the entire theater, the vast, dark, frozen sphere, extending light years in every direction, containing trillions of objects that no human eye has ever seen, reaching outward until it begins to dissolve into the gravitational territory of neighboring stars. Home is mostly dark. Home is mostly cold, hovering just a few degrees above, absolute zero throughout the overwhelming majority of its volume. Home is mostly empty, so sparse that 1 trillion objects vanish into it without a trace, leaving the average traveler passing through with no sensory evidence of its existence whatsoever. Home extends so far into the darkness between stars that the concept of our solar system as a discrete, bounded place becomes philosophically questionable. The Oort Cloud's outer reaches are already interpenetrated with the gravitational territory of neighboring stars, continuously exchanging material with the interstellar medium, shaped by forces that originate not in our solar system but in the galaxy surrounding it. Home, it turns out, is not a container. It is a process, an ongoing negotiation between the sun's gravity and the galaxy's tidal forces, with the Oort Cloud as the contested frontier, where that negotiation is perpetually being conducted and perpetually remaining unresolved. This realization does not diminish the solar system. It expands it in both the literal and the philosophical sense. The solar system we actually inhabit is incomparably larger, stranger, and more extraordinary than the one we learned about in school. It is a domain of genuinely cosmic proportions, stretching light years across, ancient beyond easy comprehension, populated by relics of the solar system's formation era, preserved in near-perfect condition by the cold and the dark, and the emptiness that would otherwise seem to make the Oort Cloud a place of pure desolation. It is not desolation, it is preservation. Every frozen body in the outer Oort Cloud is a physical archive of the solar system's earliest history, unmelted, unmodified by geological forces, by plate tectonics, by volcanism, by the chemistry of liquid water, preserved at temperatures so low that even the most volatile compounds remain locked in crystalline form. When a long-period comet breaks from its ancient orbit and falls inward toward the sun, it brings with it a sample of the raw material from which the solar system was built, a chemical snapshot of the protoplanetary disk as it existed 4.5 billion years ago, before the planets had fully formed, before life had appeared on Earth, before the sun had even reached its current stable phase of hydrogen fusion. The comets arriving in our sky are not merely beautiful, they are time capsules, messages from the beginning of the solar system, preserved in the outer darkness and delivered by gravity across timescales that dwarf all of recorded history. We are still reading them. There is a question that the Oort Cloud poses to human self-understanding, and it is not primarily a scientific question. It is a question about the relationship between knowledge and experience, between what we can measure and what we can feel. We know the Oort Cloud is there. We know its approximate size, its approximate population, its formation history, its dynamics, its relationship to the galactic tide, and to the passing stars that periodically stir its outermost regions. We know it extends to 1.5 light years. We know it contains perhaps 1 trillion objects. We know it is the dominant structure of the solar system by volume, and that everything else, all the planets and moons and asteroids and spacecraft and everything humanity has ever done in space, fits inside a region so small relative to the Oort Cloud that no diagram can represent both simultaneously. We know all of this, and yet we cannot feel it. The Oort Cloud does not appear in any photograph ever taken. It does not make itself known through any instrument aboard any spacecraft. It is present in our sky only through its emissaries, the long-period comets that appear once every few years, blazing briefly, retreating back into the darkness from which they came. Every other piece of evidence for its existence is mathematical, inferred, modeled, calculated, real in every scientific sense, present in no sensory sense whatsoever. This asymmetry between the certainty to tease assistance and the total absence of its perceptual presence is perhaps the most unsettling thing about the Oort Cloud. It means that the dominant structure of our home, the structure that constitutes virtually all of the solar system's volume, the structure that defines the true extent of the sun's domain, is permanently beyond the reach of direct human experience. Not temporarily beyond it, waiting for better technology to bring it into view. Permanently, structurally, fundamentally beyond it. Individual Oort Cloud objects are too small and too dark to be detected at their distances by any plausible future telescope technology. The spiral structure in the inner cloud, even if eventually confirmed, will be inferred from hundreds of carefully measured orbits, never from a photograph of the structure itself. The Oort Cloud will never be seen. It will always and only be known. And yet knowing it, truly absorbing what it means for the solar system's scale and nature, changes something. It changes the relationship between the familiar diagram and reality, between the solar system of human experience and the solar system that actually exists, between the comfortable, bounded, sunlit neighborhood and the vast, dark, ancient, open domain that surrounds it in every direction. The solar system you inhabit is not the one that appears on the poster. It never was. Somewhere out there right now, a frozen body the size of a mountain is drifting in darkness at approximately 70,000 astronomical units from the sun. It has been in this orbit for 4 billion years. It has never been warmed by anything. It has never been photographed. It has never been touched by any instrument or signal from Earth. It orbits so slowly that in the entire span of recorded human history, from the first cuneiform tablets of ancient Sumer to this moment, it has moved perhaps a few million miles along an orbital path that measures hundreds of billions of miles in total length. By the time it completes one orbit, every civilization currently existing on Earth will be a matter for archaeologists. From its surface, the sun is still the single brightest star in the sky. It outshines Sirius. It outshines everything. If you knew where to look, you could find it easily a sharp, brilliant point in the blackness, clearly the dominant light source in that otherwise undifferentiated field of stars. But it provides no heat across that distance. It casts no shadow on the surface beneath you. The sunlight, reaching that frozen body, carries so little energy that it could not warm a grain of sand by a fraction of a degree in the lifetime of the universe. The sun is visible and irrelevant, present and absent, the source of the gravitational thread holding that frozen mountain in its orbit and the provider of nothing else whatsoever. The constellations from that vantage point are almost identical to the ones seen from Earth. Orion still stands, the Southern Cross still turns, Ursa Major still traces its familiar outline. The stars are so unimaginably far away that moving 1.5 light-years within the solar system barely shifts their apparent positions at all. The night sky from the outer Oort Cloud looks like the night sky from Earth. You could be standing in the darkest desert on our planet and see a sky indistinguishable from the one seen from a location 1.5 light-years away. That object is inside your solar system. It is part of your cosmic home. It orbits the same star that warms your skin. It formed from the same disk of gas and dust that formed the Earth. It shares a sun with you across a distance so enormous that the sun it shares with you is barely distinguishable from the 10,000 other stars visible in the sky above it. The only thing connecting it to your world is an invisible thread of gravity, stretched to near transparency across trillions of miles of vacuum. A thread so thin that the next passing star, one that will not arrive for hundreds of thousands of years, might sever it entirely, sending that frozen mountain drifting into interstellar space to wander the galaxy alone for the rest of time. That thread is real, that connection is real, and the fact that it exists, that the sun holds that frozen body in orbit across that incomprehensible distance, that the same gravitational force that keeps your feet on the ground also holds 1 trillion frozen mountains in orbits 1.5 light-years away, that the solar system is not the compact planetary cluster of the classroom diagram, but a vast, dark, frozen sphere of almost unimaginable proportions, with a tiny, warm, luminous core at its exact center. That fact is one of the most extraordinary things science has ever revealed about the place you live. You asked, at the beginning of this journey, how big the solar system really is. The answer is this: it is mostly darkness. It is mostly cold. It is mostly empty in any sensory sense, populated by trillions of objects that cannot be seen and have never been touched. It extends for 1.5 light-years in every direction from the sun, possibly farther. It constitutes a gravitational domain so large that even light needs more than a year to cross it, and our fastest spacecraft would need 30,000 years to traverse it. Its dominant structure by volume, the Oort Cloud, is also its most invisible, most ancient, most diffuse, and most extraordinary component. Its outer boundary is not a wall but a gradient, fading gradually into the gravitational territory of neighboring stars, dissolving into the Milky Way rather than ending against it. The solar system is not a neighborhood. It is a galaxy-embedded gravitational empire, mostly dark and mostly frozen, with a small, brilliant, improbably warm interior where, on one particular rocky world at one particular distance from one particular star, the frozen darkness of the outer solar system is as remote as any place in the observable universe. And yet that outer darkness is home. It has always been home. We simply never looked far enough to see it. The familiar diagram will look different to you now. The 8 planets arranged around the sun, that neat, orderly, satisfying image will carry a new weight, because behind it, surrounding it, dwarfing it in every conceivable dimension, stretches a frozen sphere of ancient ice and dark rock extending outward into a night so deep and so cold and so silent that nothing in human experience can prepare you for its true character. That sphere is the solar system. The planets are the ember at its center, and the ember, for all its smallness in the vast dark hole, is where something extraordinary happened, where the frozen chaos of the outer solar system somehow, against every expectation, produced a warm world with liquid water and a thin, breathable atmosphere and, eventually, a species capable of looking outward at the darkness and asking how far it goes. We are still asking, we are still learning, and the darkness, patient, ancient, incomprehensibly vast, is still answering, one comet at a time,